Yo, 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 can you guys hear me? Yay! Yes, sir! Alright, kill that now. Just making sure the sounds and everything are doing what I expect them to do. Sound be good? Sound be good. Okay. Just making sure that nothing's interfering behind the scenes. Can you guys hear me okay over the volume of the musics? I assume that the respective volume differences are okay. Yep. And what's up? Now let me just try and adjust the old cameras a little. Yeah, that'll do. Yeah, volume balance good. Excellent. Excellent. How are you guys going? You alright? Is everything going alright? There we go. Black on black. Yeah, I've got a black t-shirt, black figure 4 t-shirt, black t-shirt. I've got this is actually like a dark blue, but in this light it may as well be black. As you can see, I haven't had a haircut for ages. I haven't shaved, but I have had a shower because I was incredibly sweaty before. But anyway, it has been another few weeks since we last got together, and a considerable amount of time since the last time we got together for this reason. So, anyway, greetings to everyone. Seskar, Archbishop, Sisop, Atwolf, Binchuk. Who's that? Bizmeme? Men's, nice to see you as well, mate. Serializing's on as well. How's it going, ladies and gentle peoples? I hope you're all holding up okay. I'm going to turn a little bit down in my ears because that is quite loud for me. But yeah, doing good at this end. Doing good at this end. Been very busy times. Lots of crazy things going on. Benzies! Benzies! I thought you'd be streaming yourself tonight, mate. Doing your wheelies and whatnot around Stromlo. Is that not on the cards? I think... Sysop, you don't get ads because you're a sub? Twitch Prime sub? Yeah, pretty much. I think that's why. Most people who aren't subs don't get, they get ads jammed in faces and stuff. But it is what it is. Anyway, yeah, so as I was saying, it's been a while. Been a while since we got together. The last time we did some more development, we actually made some progress on our named pipe pivoting stuff from a terp. However, it has been a long time since we've done a PicoCTF challenge, and I thought, you know, people love the hacks, people love the binary stuff. I thought I would give this a crack for something a little bit different. All the trails are soaked, that's a bit crap. But before we continue, we have to address the most important things. Remember that hacking without T is very uncivilized. So tonight, I know that Seska is going to appreciate this. I filled up on Gyokuro earlier today, so now I am back on the Dongding Oolong, which is more of a short-term drink. You don't want to let this one go all day. Thank you, Benzies. Your support, regardless of whether you're a sub, is very much appreciated. Now, also for the first time in quite some time, I decided to break out the chocolate, and we're back on the 95%. So for those people who are out there with their respective beverages, I hope you have a nice little tot of something sensible like this to go with it. Can we call it Ding Dong Oolong? You can call it whatever you like, but that doesn't mean that you'll be correct. Or as I like to say, I'd agree with you, but then we'd both be wrong. T2 Green. Hey, Zocap. Good to see you, dude. And here I am again, taking a mouthful and speaking, which I was told from a very young age is the wrong thing to do. Sorry about that. Just noticed the oh, Rust is back as well. Good evening, sir. Thank you for the sub. I just noticed the auto mod thing going on in the chat. The word dong was blacklisted, but in this context, it's completely legitimate. Thank you, Atwolf, for sorting that out. Swappage, good to see you, mate. Haven't seen you for a while. Tell you what, this stuff is so tasty. Really, and it goes so well with green tea. Anyway, I think I say this all the time. I really shouldn't. Talk with a mouthful of marbles under... I agree. I know that I am able to talk a lot. Right. On with the show. The business. Ooh, who we got? Richie 10. I think that's what that says. Thank you very much for the follow. Welcome to the stream. Yeah, so what we're planning on doing today is a binary exploitation challenge from PicoCTF 2018. Now, given that it had been quite a considerable period of time... Ooh, what's going on? We got some subs. Oh, mate, Rasta's dishing out the sub gifts. Thank you very much, Rasta. You are a very generous individual. Rasta, the man behind Rasta Labs. You should go and use his gear. We are not officially affiliated, but I genuinely think his stuff is legit. So go check it out. Anyway, I mean, I don't like the guy. He's a jerk, but you should go check his stuff out. Yeah, so this challenge we did, I think, squiz at briefly at the end of the last PicoCTF stream, but part of the reason that we didn't do it is because there were actually not that many solves and it looked really hard. So, hey Civilized, welcome to the stream. Good to see you again. So anyway, we kind of put that on ice and then we went back to Materp Dev and, you know, things went off and it's like, okay, let's go back to doing some old school memory exploitation hacking stuff. So in firing up my VM to make sure that I had done all of the bits and pieces to make sure things would work, I thought I'll pull down the binary and make sure that it runs. Because there's nothing worse than spending the first however long on stream trying to get things to run. For Christ's sake. Oh, hey, Will. How you going, dude? Nice to see you, mate. Or is that Dad speaking on your behalf? Hey, Peleus. Thanks again for coming on, everybody. It's always a pleasure to see you all. Yeah, so it looked pretty hard, and I'm super glad that I did. So last night, I was trying to get this binary running on my host, and it just kept crashing. And it wasn't intentional, from what I can tell. So I spent a bit of time spinning up a Docker container that matches the target operating system and wiring in all the pwn tools and all that sort of stuff so that we could actually do this on stream. So other than that, I haven't done anything, and you're gonna have to take my word for it. Let's just pop me back up there. Okay, so as you can see, this free calc challenge, this is the one we're going to do. Now there's only 71 solves of this thing, which is a little bit concerning. Dr. Shush, hello. Punisher, greetings. Lovely to see you all. Man, the milkshake has brought all the lovely people to the yard. Anyone would think that they love hacking. Yeah. So, anyway. Yeah, don't you start, Benzies. I'm not here for the trolls. So I've set up a Docker container that's going to allow me to do the hacks actually on an operating system that it doesn't crash on, at least not intentionally. So other than that and getting the shell of an exploit together that automates it, I have done nothing. And now, bear in mind, this challenge was from 2018. 71 people have solved it. I don't know if anyone on stream or in the chat has solved this before. So what I will say is we're going to have to work on this together. I'm pretty concerned that I'm not going to get very far on this thing, given how few solves there are. But the important thing here is if you have solved this before, please don't give us spoilers. Like, I want us to collectively, legitimately pop this thing on stream. Okay? So I'm super keen on ideas and thoughts from anyone who's on stream, as long as you're not cheating. So if there are write-ups out there, please don't go and read them and then offer little snippets of advice. We want to go completely clean, legit. Okay? All right, so what I've done behind the scenes was I pulled down the stuff. And you can see we've got calc, which is a binary. Okay? That's a 64-bit non-stripped executable. We have the source, which is a bit of a win. We've got this libc.sh .so, which clearly is the one that's being used on the target, and we've got the shell of exploit ready to go. Yeah, I don't know what to expect either, but I'm pretty certain it's going to be rough. I mean, some of these other ones that were quite cute, they've had a lot of solves. This one really hasn't, so yeah, expect a bit of pain. Now, there's always something about the names that are a bit of a giveaway here. I remember when we did Can You Get S Me? Clearly that was abusive get S. This is called Free Calc, and it says things are heating up. Can you help us exploit this program and get us the flag? Clearly it's going to be running on this target machine. So Free Calc, I'm assuming that we're going to end up having something to do with free. That would be the go. All right, so what I have done is I have this Docker container that I've called Pwn Xenial, and Xenial is the target operating system. So if I run this, you can see I've got tmux running. We're in the /pwn folder, and the stuff that's in the folder is what was on the underlying operating system folder at the time. So from here, if I run calc, this is what we get. Welcome to heap calc. This is a postfix calculator. So we can do plus, multiply, minus, divide equals. I wonder what this hash symbol means. So example 1 equals outputs 2. Okay, so you guys, I would assume everyone knows what a postfix calculator means, or what the word postfix actually means in this context. All right. Oh, the font's tiny. Is it? Should be exactly the same as the last time. Hang on a second. Is everyone else having issues with this too? Let's do... Where is it? Is it this one? I don't think it's that one, is it? I've got to go to profiles. There we go, this way I got it. So let's go up to 15. Is that better? Oh, okay. Anyway, we'll leave it at this size regardless. That's not going to be a problem. If it gets too big and we're cramming too much on, trying to get too much on screen, I'll reduce the font size again. Okay, so what I think we should do at this point is have a look at the source. Whoops, not the binary. That's not going to help. Okay, so what have we got here? We have a bunch, we have enumeration, we have a bunch of type defs for structures. Parse op. Okay, memory, we got an xmalloc, so helper function. That looks like it exits when malloc fails. We've got an xrealloc, which does exactly the same thing, just exits when realloc fails. What else we got? We got push. Right, so this just pushes a value onto the stack, whatever the stack happens to be. So let's have a look at the definition of stack. So a stack has a value and a reference to the next element on the stack. So it looks like almost like a one-way linked list. Nothing particularly special going on there. Alright, so when we push something onto the stack, we give it a value. And it creates a reference to a stack object, allocates the stack object, shoves it at the top. Now, what's interesting about this? Yeah, right, okay. So stack T is, okay, so that's just a pointer to a stack T object. Ah, type, there you go. Okay, so a stack T is actually a pointer to a stack element. So that's how that actually works. So you get a reference to a stack T, which is actually a pointer to a pointer, and that is a pointer to a pointer of a certain type, and that type is a stack element. So does that make sense? So you got stack elements and then a pointer to the topmost stack element, and that's what this stack T type is. Thank you for the follow, Tijo. Appreciate that. Welcome to the stream. So popping clearly does exactly the opposite. Now, what's interesting about this? Oh, it actually returns the value, not the actual stack element. So popping moves the stack pointer down one, pulls the value out, frees the stack element, returns the value. Jay's in the house as well. Greetings, Jay. Good to see you. Rusty, you don't hate C. So let's just think about, okay. Think about like C being what P invoke should have been, and that should make you happy because you love P invoke, right? Yeah. See what I did there? You're welcome. All right, so what do we got here? Define function. Python 3 all the way. Woo, gross. He does, doesn't he? So he loves the P invoke. How many exploits would we not have without C? That's a very good point, Peleus. So what's this? This define function thing looks pretty complex. We've got this funcdef t. What is that? A funcdef has a name. It has what looks to be a number of operations and however many operations there happen to be. So an operation is what? Let's type that straight. An operation has a value and an opval, which is one of these opval t's. And an opval t is a union of either a value or a function definition. Yeah. Okay, so that's interesting. So straight away, this stands out to me. Union. Now, what's really interesting about this is that in one context, you guys know what unions are, right? If you don't know what a union is, please type F in the chat to pay your respects, and I will explain what a union is. If no one taps F, I won't bother. Men's, what's a union? Okay, so a union basically says that there are multiple values that take up the same area of memory. Yeah? So what this means here is, if you look on line 22, you can see that it is of type long. Okay, so ival is of type long. Then on 23, you've got this fval, which is a pointer to a funcdef of t. Now in 64-bit, both of these values should be 8 bytes, right? So what this means is, I'll just butcher some code directly in line here. Let's pretend that we actually had an opval t type here called foo, okay? So what this would mean is, if we actually set, for example, let's go foo.ival equals 0. Okay, so what that's doing is that it's treating this memory space here, which is all the same, as a long, right? So if I went, for example, foo.fval and I tried to dereference that, that would break because ival and fval are on the same memory space. So by setting ival to 0, I've actually set fval to a null pointer. Okay, so it's kind of like those two values are sharing the same memory area. Okay, so if you modify one, you're actually modifying the other. Does that make sense? It's like a struct, exactly. The difference is that everything inside that union all lives at exactly the same address. Okay, so another way of putting it is this: foo.ival, the address of that is the same as the address of foo.fval. Okay? Does that make sense? So, and that would go with however many values you put inside the union. Now remember, you can have unions inside unions, you can have unions inside structures. It's just a way of saying, you know, when I know that something is of a certain type, I can just treat that memory space as one type. And then, if it is of a certain other type, then I can just reference it. It stops you doing the nasty casts yourself, but it clearly opens the door for awful things. Now, the reason why I think this is interesting is because, see this, if this is a union, right, and this funcdef t actually gets set. So it is a pointer to something. Let's say it's a pointer on the heap. If we can trick whatever's using this into thinking that this is not intended to be a funcdef, but instead a long, and we can read that value out, then maybe we have the means to read a pointer out of the application. That might give us a memory leak, for example. Yeah? Is it possible to put elements of different sizes within a union? Great question, Peleus. The answer is yes, but the union will always be the same size. So it will be the size of whatever the maximum value happens to be. Okay? So in this case, I think long might even be 32 bits. Funcdef is 64 bits. They will both be effectively taking up the same memory address. And so it'll look at the value inside the union that is the biggest type, and that's how much that will take up. That's how much that entity will take up. RFC Hacks. Ooh, RFC Hacks, nice. Thanks for the follow. Welcome to the stream. So that's what that means. Basically, we have the means to reference multiple variables that point to the same area of memory and that have different types. I hope that makes sense. Now, there's a bunch of these in the Windows API. And they can actually be super handy. Like, you can use them to get to internal values of certain things. So let me just wind this back to here. So like if you had a type def union foo, okay, so something in here, then what you could have is a union in here, which is of, let's call them bits. Okay. And you could have a short A. Is this what I want to do? No, that's not what I wanted to do. You could have... What am I... I'm trying to do this off the top of my head and it's not working. So I want... what you effectively want to have is two shorts. Right? So we've got... short A and short B, like that. And inside here, you have a union, we'll call this bits, right? And inside here, you've got a long, we'll call that C, and you have a struct, which is basically of another type, called something else. And so what you can actually do here is inside this union, you can get to C, which gives you the 32 bits, and you can reference fds.a and fds.b as the individual shorts. So you can kind of easily dissect the whole long value into its two shorts, if that makes sense. That's a pretty horrible bastardized example, but that's how you can use unions to easily pull values apart. Does that make sense? Was that helpful? I'm assuming it was. Now I'm really hot because of my tea and the lights and this jumper, so excuse me a second, I'm going to remove the jumper. Ooh. Should have preempted the stripper jokes. Okay, so does everyone know and understand what a union is now before we continue? Now I would assume that this opval t, you see this long t and opval t, I would assume that this long value is going to be this op type. So if we can change this op type, let's pretend it was a constant, right? So if you had this operation that was a constant, the constant goes here, and the opval is either a value or a funcdef, okay? So the value here, you would assume that if it is a constant, it's going to return a value based on ival. But if it is a funcdef, then it'll return the opval based on funcdef. So I would assume if in memory we had a funcdef and we could trick this into thinking it was a constant, then it would return this as a long and maybe spit that out to screen. Yeah? You guys are awful. God. Far out. Anyway, let's move on. You jerks. Okay, so here we can see we've got a maximum number of functions that we can define. There's 16 of them based on this definition. So we can have 16 separate function definitions, which I assume are based on name. Lack of comma is unfortunate. Yeah. Okay, so that's that was this define function that kicked us off there, right? So let's have a quick squiz at what this is doing. So it's going through what looks to be the existing functions, right? And if the functions are the same, okay, check if function names are the same. So function already exists, basically means matches based on name. Then we get a reference to the old function definition. And if there are more operations, we realloc the old and then copy the new ops to the old ops. Okay, so that is effectively overwriting the old function definition with the new one. And then what is it doing? It's freeing. It's freeing? Just work with me for a minute here. So something is not quite right. Now remember this, see how it says resize the ops array. So this happens when you've defined, assuming that we will understand in a minute what it means to define a function. Each function has a certain number of operations based on this line number 93. It's comparing if the new function definition has more operations associated with the old definition. And if that's true, then it needs to reallocate space based on the number of operations in the new one, right? And then it copies these ops to the old one and frees up F ops. Okay, so what I was trying to understand here was, is there a need to free? Yeah, so if it clashes, then it frees. Okay? If the function has not been defined and we still have a space, we basically just insert it into the array based on that identifier. Okay. All right. Okay, that's okay. What's interesting though, I reckon there could be something in here. I mean, there's 3 calls to free here. It'd be interesting to know whether or not free calc has something to do with this stuff being abused. So we must come back to that. So realloc, remember, will take whatever memory you've given it and reallocate enough space based on what you then request. Realloc should also copy the data over for you. Anyway, so yeah, so if the function definition already exists, we free it. Okay, so the question then is, where does define function come from? Define function op val. Okay, so this run operation is the only place that's invoked from. Okay, well, we'll come back to that. Are there any questions? Ah, okay. No questions. I'll assume that I'm doing everything correctly and that my definitions and descriptions are just sublime. So, until further notice, that will be my assumption. Alright, so what does this read function do? Okay, so clearly this is a function that's intended to pull a function value out of thin air, given that there's no parameters passed in. What do we got here? No. Invalid function name. Oh dear. Oh, it's using strtalk. Gross. You guys familiar with strtalk? It's important to understand what's going on here. The library function strtalk breaks a string into a series of tokens using the delimiter that we give it. So the first value is the contents of the string that we want to tokenize. Okay, so, and it actually modifies that string, as you can see. So based on the token that you're searching for, it'll actually, I think, overwrite that token with a null terminator so that you actually get that piece of the token. So if you had a string full of spaces, then and you wanted the words, then you could use strtalk or talk and say, I want to break based on spaces, and it will overwrite the spaces sort of as you go with nulls to give you the individual words. Yeah. It's not really dot split, like, and it's probably really important to delineate between what dot split and what this actually does. Split returns an array with each of the components in it and doesn't modify the original string. This modifies the original string. Okay, now this is actually super important because there is a special case here. See, the function returns a pointer to the first token found in the string. A null pointer is returned if there are no tokens left to retrieve. Now, this is super important, right? Have a look at this. So strtalk maintains state behind the scenes that is reused. Why is it so bright? Does this make sense? So what that means is you call strtalk with a string and it returns, as it says here, a pointer to the first token found in the string. Then subsequent calls, you must pass in null, right? That means it's going to use the previous reference to go to the next token. Okay, so it's stateful, and that's why strtalk is actually not thread safe. So there are thread safe versions of strtalk, like strtalk_s, but they're not thread safe. It really is disgusting, right? So this is a standard C standard function that tokenizes a string, modifies the string that you give it, and maintains state behind the scenes for you, which is just horrendous. You don't even give it state to modify. Yeah, it really is. It really is. But, you know, it is what it is, right? So that's why I wanted to dive into that, because as you can see, this read function assumes that strtalk has already been called. It's already been called. So it's not passing in its own, yeah? It is a function that keeps on getting. All right, so this assumption here with read token is that strtalk has already been called once. Now let's have a look. We've got this scanf, and then that's being invoked from parse op. Interesting, hey? Hey OJ, is there certain exploits that you would not be able to create without writing it in C? If so, example. There's certain exploits that you wouldn't be able to do if you didn't write it in C. I don't think so. I mean, you probably couldn't write an exploit in brainfuck with any ease or in a short period of time. I think there are some things about writing exploits in C that make certain memory corruption things easier when you're dealing with things like Windows APIs. You do have the facility of dealing with Windows APIs in all of the other languages. Like you could do it in .NET, you could do it in like any of the .NET languages, you could do it in Python, you could do it in Ruby. As long as there's a way for you to invoke the APIs or the functions that you need to invoke, right? If you're dealing with them remotely and you're just connecting to sockets, then it's no big deal. But if you're dealing with sort of local memory corruption, you probably find that for the most part, dealing with the APIs directly in C would make things easier. If you're dealing with COM objects, and you're still doing memory corruption, then you might find doing it in C++ is a little easier. But then again, you could probably just do it in VB or C# and still deal with things the way that you would expect to deal with them. You would just possibly have some marshalling shenanigans that you need to worry about, you know? I think it's fair to say, like, if you're dealing with race conditions, it probably makes the most sense. But at this stage, I can't think of a reason why that you would not be able to deal with an exploitation path in any other mainstream language, assuming that that mainstream language has the ability to interact with the APIs that you need to interact with, basically. For Christ's sake. So why did the first two words go on the line and then the others were separated? Ah, yes. So that back to the example here. So we're looping through and we're printing out the string followed by a new line. And you can see that the separator was this. And so there are spaces here, right? So you can see that it's actually captured the spaces as well. Yeah. So if you pass in, yep, and you get a pointer back to the start of yes, Peleus, that's effectively it. Now, there's one thing that I'm not 100% clear on, which we can probably check when we go through this, and that is whether or not it actually tokenizes the entire string up front, or whether it just does it on the fly. So it might search for the first token, set it to null, and return a pointer to the first one. And then, when you call it again, it unsets that null and then does the next one. But I'm not exactly sure. Why are there two spaces? Good question. So you see the printf, there is one space in here in the format string, followed by the one space that's after the token. So that's why there's two here. One for the printf and one that's actually either side of the token. Okay, hopefully that makes sense. Righto, so back to the codes. So read function assumes that strtalk has been called. Let's just have a quick look. Ah, here we go. Look at that. So there's this assumption that in the main loop, which we'll cover in just a minute, it's actually tokenizing the string. In fact, let's do this while we're here. So entry point looks fairly typical. The first thing it's doing is turning off output buffering. That's some hack that you always do to have C stuff sitting behind a service like xinetd so that it always spits out the characters as they're rendered rather than buffering them, to make sure that there is like almost directly interactive communications over the sockets. So that turns off buffering. Print, welcome heap characters, postfix calculator, blah, blah, blah. And then loop ad nauseum. And what do we do here? So we have a line, get line. So there is a function called get line. And get line says, go and get a line from standard in and give us a reference to the memory and however many characters, I would assume. I think getLine's a library function, isn't it? Yeah. Okay, let's have a quick squiz at the documentation for that. See getLine. The getLine function. Have we looked at this before? Oh, this was actually in another exploitation challenge. So the latest and most trendy function for reading a string of text is getLine. It's a new C library function having appeared in 2010. Okay, so it's prototyped in standard I/O. Buffer is the address of the first character position where the input string will be stored. It's not the base address of the buffer, but the first character in the buffer. This pointer type or a thing, causes massive confusion. Okay, so size is the address there that holds the size of the input buffer. God, I tell you what, this has got one of those JavaScript scroll bars or something. It's awful. Okay, so right. So you do have to allocate a buffer, then call getLine and say, this is the this is gross. This is really gross. So you see here, you allocate a buffer and you get a pointer to a block of memory, and then you put the address of that into getLine. Ugh. Hang on, I'm going to go and read another definition of this, just to see if there's any nicer Get line. POSIX library function allocates a buffer to hold the line contents and returns a new line. The number of characters in the line and the size of the buffer. Right, so in this example, there is no malloc. That's what I thought was weird, because the previous example that we read allocates memory first, which is nonsense, because then you're actually leaking memory. Hang on, let's go back. So that one there. So getLine actually allocates the memory for you. But this Muppet is allocating memory and then saying, give me more, so that this malloc call ends up leaking. Let's not follow that example. Okay, that makes a bit of sense. Oh, there's even a getLine in C++, which is probably memory safe, which the C1 tends not to be. So I get the first line of the file. So for each one of these, I would assume, oh, hang on, what are we going here? Free the allocated line buffer. So if you pass in a pre-allocated buffer to getLine, does it free it for you? Oof, man, this is horrible. Yeah, tell me about it. Hey, like, it's just rough. So that frees, you see how you would assume that this will either be reused or maybe reallocated. I'd love to know the actual, I wonder if there's a, let's see if tutorials point can come with the goods. Tutorials point getLine string. Is this what we want? Nope, that's using C++, which we don't want. We want the C version. Yeah, the docs on this are really not that clear, are they? We don't want the C version, C++ version. We just want the C version. Delimited string input. Here we go. Here we go. Linux man page for the win, right? Memory leak POC top Google result. Oh, really? That's rough. Okay, so reads an entire line from the stream, storing the address of the buffer containing the text in here. The buffer is null terminated and includes the new line character if it was found. If this is null, then getLine will allocate a buffer for the string, which should be freed by the user. Can contain a pointer to a malloc allocated buffer. If the buffer is not large enough, it's realloced. There we go. Should have come here first. In either case, on a successful call, they will be updated to reflect the buffer address. Right, so realloc calls are actually happening behind the scenes if the buffer's not big enough. Yep, excellent. Thank you. I have no idea how to say your name. Kekemodalwieko. Thank you. Sorry, that was a mouthful. Yeah, okay. All right, cool. So we start off with nothing, and then we say go and read a line from standard in, and line will then contain a pointer to a buffer that's big enough to contain the line that's read, including the new line and a null terminator. I would assume that this returns the number of characters that are actually read or some kind of error value. Let's quickly look at what the return value size t. Return value on success. Return the number of characters read, including the delimiter character. Okay, so that means that this n refers to the size of the buffer, not the number of characters in it. Hey, multi. If there's a new line, then terminate it with a null. Okay. And then we begin our tokenization. And we say, okay, op string, parse the op. So I assume the operation would be like a plus or a minus or whatever it happens to be, or perhaps just the whole line. And then if it worked, then run it. And then continue. Huh. Okay, so does that mean you can... The implication there would be that you can do multiple ops per line. All right, so the example they've got here, 1, 1 plus equals. Okay, so that's taking the first two and spitting the result out. Okay, so if we went 1, 1 plus, and then we did like 3 plus equals. Ooh. Ooh. Accidental crash. Double, free, or corruption. Rip. Okay, that's interesting. So does that mean, like, if we run that again, if we go 1, 1 plus equals, and then we go 1, 1 plus equals. Yeah. I'm pretty sure this is intentional. Yeah, wow. Okay. All right. So, but yeah, so clearly we can do, we go 1 plus, 1, 1 plus, and then like 4 plus, and then equals. Yeah, okay. So you can kind of combine your operations as you go, and there's some kind of stack behind the scenes that does it. Yeah, that wasn't even an invalid postfix expression. I know, right? That's crazy. Crazy town. All right, back to the source. Okay, so why are we getting a double free? Oh, I see it. Do you see it? I'm gonna have a sip of tea. Can you see the double free? No? Anyone? Can anyone see the double free? I can see it. Pick me. I can see it. It's just there. You see it? Where is it? So, obviously one of the frees is on 297. Where is the other free? It's there on screen. Bingo. I hope we've all learned something. Where is the other free? See, this is why we read documentation. It's in here. Remember, getLine will realloc. Ah, yeah. So remember that reallocs, which is the same as free and malloc. And here we're freeing. So I would assume then, if we do this again, hang on. Yeah, so if we instead did, see how we've done a long string here. If we do a short one now, 1 plus 1 plus, that still dies. Why is that? I was kind of assuming that if the buffer was going to be big enough, then it wouldn't free it. But anyway, I think that's what's going on. We'll debug it shortly to figure that out anyway. But that's interesting nonetheless. So we're clearly freeing in getLine and freeing here, unless there's another free going on, which wouldn't make any sense at all. I would still do a second free at 297. Yeah, it's still, well, yeah, the assumption would be, so it allocs here, it calls malloc, and then frees. And then when we call getLine again here with the same buffer, I would assume that if it's smaller, that it would not attempt to realloc, it would just reuse the existing buffer. Yeah? That's kind of what I would assume. But anyway, we'll come back to that. Parse, I mean, we don't, based on this, we don't really get that many attempts to own it in one go, do we? I'd assume that all the other operators work fine. So if we go we'll go 10 times 10 No, can't do that. We've got to go 10, 10, then times. And then we can like add 3, times that by 3, and then get the result. Now, this buffer size is clearly this big. So if I then did 1, 1 plus equals, my assumption based on the code that I'm seeing here is that line is big enough to hold the data that's coming in from standard in, and n is bigger. And based on the documentation that we read here, if it's null, a line pointer can contain a pointer to a malloc allocated buffer, n bytes in size. If the buffer's not large enough, it's realloced. So my understanding would be that that would work, but it's not. So get line free. Oh, yeah. My bad, dude. You are highlighting a really important point here. Double free or corruption. It'd be this part, wouldn't it? It's interesting. I'm getting different. Yeah, okay. Anyway, so clearly this is a bug that's worth exploitage. This would have to be our entry point, yeah? Correct. Peleus, it does have it outside the loop, because when you're out of the loop, you know you're not going to be calling getLine again, and whatever's left over you need to free. So that makes sense. Okay. Make sure you provided libs. Ah, that's a good point. LD preload. Pwn libc.so.6 calc. All right, let's try that again. See if it does anything different. Right, it's the same. Yeah, I deliberately made it so that this operating system was the same as the target. So the versions might actually be very similar, if not exactly the same. Anyway, we're already nearly an hour in and we haven't really done anything. Okay, so we tokenize the line and then we say, while we're able to tokenize it, go and parse the operation. So let's go see what parseOp does. Okay, so we attempt to read an integer. So scanf, we say give us an integer. Well, LD is what a... Is it a long? I think it's a long. See ya, swappage. Yeah, so we try and read a long into constant. And scanf should return the number of successful reads. So if the number of successful reads, is 1, then we can say, hey, we have definitely read a long. So we're going to, with this op, we're going to set it to, okay, so the type is going to be a constant. And see how here we go, we're referencing ival here, see? We're not referencing fval, we're using, this is where that union thing kicks in. So we're setting the long value, right? Now, we then check the op string that we've pulled out from before. If it's not, so in other words, if it's not an integer, what is it? So if it's not an integer, it can be any of these things. Nop equals blah, blah, blah. If there's a colon, then we've got a function definition. At which point we would then go and read the function definition. Now, if none of those match, then what are we doing? We're going to iterate through our function definitions and we're going to check to see if any function matches based on the name, at which point we're going to pull that function out and put it in the operator. Okay, that's interesting. So does this mean we have multiple references to the same function? Yeah? I would assume that when we define a function, Yeah, we read a function out and that gets stored in the stack of functions, right? Here we're going through the existing list of functions and storing a reference to that function. Ooh. That is also very interesting. All right, so assuming that we end up with like multiple references to the same function in the same line, is there some way we can abuse that maybe down the track? Who knows? But what happens at this point is this parse op returns an indication of success or failure based on whether it was able to parse that out. And if it's true, if it returns true, then it says run it. So op is on the stack. We're just populating that. Let's go back. Is there any, there's no mallocs or anything going on here, is there? No, there is not. It's just read. Ah, this one here. Read function. There's an alloc that goes on behind the scenes, but yeah, okay. So this is not responsible for allocating anything directly itself. Okay, so what does run op do? Okay, so what we do is we give it the reference to the operation that we've just read, which could be a constant. It could be a function, it could be any of those things. And then it says, okay, so if it's a constant, all we're going to do is push the constant value onto the stack. If it's, we'll come back to the function def. I just want to see what the other one's doing. If it's an add, we pop two values and we push the result. Yep. If it's multiply, pop two, push the result. Subtract, pop two, push the result, etc. Equals, we actually pop that, spit it out to screen and break. There's this we've got funcdef. We need to define a function. We'll come back to that as well. So if we're actually invoking a function, what happens here? Okay. It actually just runs the function as if it's its own op. Okay. So does that mean then when we run this, using this example, we've got add one plus. If we went add, takes one parameter, and defines the function add with one operation which executes plus. So how do you use it? Add 1, 1. Okay. Maybe you have to go add 1 plus. So then we want to go 1, 1, add. Oops. Okay, so we need an equals at the end to get the result, right? So that should be 2. Okay. That makes sense. Okay, that makes sense. Any questions about that? Did that make sense? So that's how the op actually runs. Okay, so let's see what this define function does. Again, we have had a quick... we've been here, haven't we? Yes. We have been here. Not exactly the most user-friendly calculator. I would absolutely agree. Postfix stuff is a bit of a mind job at the best of times, hey? Alrighty. So the question then is, how can we abuse what's going on? I think it's fairly clear what's going on. I mean, this attempting to pop an empty stack. Let's just have a quick squiz at where all the free calls are happening. So here we're freeing a stack element. I would assume that a stack element is malloc. Where are we? Xmalloc. Here we go. There's a stack element being allocated here when we push Yeah, so we airlock when we push, and we free when we pop. Is that the one that we were looking at? Yeah, it is. Okay, so that's fine. Stack. So that's the only place where we're mallocking a stack element, yeah? And then that's the only place that we are freeing a stack element. Which makes sense. Check if function... Okay. Doesn't look like there's anything particularly fishy going on here, hey? What do you reckon? Like, on the surface it seems sane, but then again, a lot of these tend to seem sane, don't they? What are you guys thinking? Like, clearly in order to get past this, there's a corruption going on. We need to stop the corruption from happening if we want to keep doing things. So what do we do? Any ideas, people? Just changing the chat window so I can see. I was hoping for ability to underflow operand stack, but it doesn't seem to be the case. Yeah, I don't think that's the case either. Maybe we should... Yeah. Okay, how about we do this? Let's just... I don't even know whether I've put ptrace on here or not. Yeah. That's pretty shithouse. I don't have any of these things. Something that I forgot to add. And I'm buggered if I'm rebuilding the container behind the scenes while we're doing this. Okay, so that's something to add to my toolset. So I assume like what we need to be able to do, I mean my first concern is how do we stop it from crashing? How do we stop it from crashing? What are you guys thinking? Be super quick if you rebuild, as it would only add the new stuff. That's actually a possibility. While it's running behind the scenes, maybe. What do I need to install ptrace? Where is that? Does anyone know the library in Ubuntu that has ptrace and strace and those kinds of things? Unless you have a compiler all from source. Need to prevent the double free if you exploit it. Yeah. So we kind of, I guess... What do we need to do? I'm trying really hard to think about what the entry point for this would be. Need to prevent the double free. Well, I mean, yeah, no need to prevent the double free if you exploit during UAF for the second free. Yep, would agree with that. Thing is, there are some mallocs that go on behind the scenes, right? So if we free here, the next thing that happens is get line, so one would assume that it's corrupted at that point. Ah, hang on. Let's do a bit of debugging. what I'm going to do actually, I'll vim this. So here you can see, this is something that I whipped up yesterday so that we were kind of ready to go. All I've done is kind of configured this so that we use the library that we were given and that I've got Team Mux Shenanigans ready to go. So that means in here I should be able to run sploit and we end up with all this kind of stuff. Okay, so if in here I go 1 plus equals and then 1 plus equals again. Right, okay, so this is where it's actually kicking in and saying fail. I know, is that really hard to read? I didn't really think about that too much. I don't want to fight the themes. That's fine. Okay, cool. All right. So, question then would be, let's have a look at. Right. So in main, we want to stop here at main plus 381, and I also want to stop at. Where is it? None of the puts is get line. So I say we stop here. Plus 193. So if we go break main 328, does that do the thing that we want? 328, yeah, okay. So we want this. Let's go. And what was the other one? I want to stop at this free call, which is 381. 38. Oops. Okay. Now the reason why I want to do this is to make sure that we can kind of narrow down exactly when things are failing. Yeah, this song is wicked. It should be listed in the chat, in the stream somewhere as well. Okay, so let's just save that and run again. Okay, so we've set our breakpoints. 1 plus equals. Okay, so we are calling free at this point, and that hasn't failed. Okay, now we're going to call getLine again. And if we just go 1 plus equals. Ah, that hasn't failed either. Okay, so that didn't fail either. So it's not failing on the get line. That's very interesting. Let's find out where it is failing. No, it crashes regardless. So when we call str toc, that's fine as well. And then when we try and parse the op, that comes back with success. Yeah. Okay, I think I see it now. Yeah, so we are reusing the existing memory, I would assume, that has been freed with the stuff that's in here. And because realloc wasn't invoked in this case, it just assumes that the memory we've given it is okay. So we are currently using it after it's been freed. And then in a second when we've done the stuff, we'll call run off, and this should succeed too. And then when we get back to where we were, pause. So let's continue. And we're back at free, and this is where it's going to die. Yeah, okay. That makes way more sense. Okay, is everyone on board with what's going on there? I'm going to change this slightly. I'm going to run it again. This time, we're going to go 1, 1 plus equals. And then this time, we're going to see if we actually get any further. So we're going to go 10, 100 times equals. So the string is bigger, so a realloc should happen. And that's okay. And so this free won't fail. Or will it? No, that free won't fail. Oops. Yeah, that free will fail. Ooh, it's so confusing. Right, okay. Anyway, I think... Okay. I'm kind of getting an idea of what's going on here. Question that I would have is there a maximum value for however many ops that you can have? Do I want to just remove it? No. Hey, Old Sound! Good to see you, mate. So, resize the ops array. Okay, so this is to do with function definitions, which I'm not too worried about. The thing that's appealing to me here is that because there's an allocation that happens when we define a function, right? When we define a function, that's where this fval is used. Read the function. Read a function here. This thing here. We're actually mallocing. So, do we have the means here after the free? Do we have the means of effectively, with this malloc, can we get the allocator to return the same amount of memory back? Does that make sense? So we actually return the point, so it's no longer breed. It's actually back in use so that the free doesn't die next time it happens. Do you know what I mean? Yeah, that's kind of what I'm thinking. Yeah. I think that is what we should be looking at. Okay, so just for shizzins and giggles. Now, we're going to start putting some things in here, right? So, okay, so the first command we're going to send, we're going to, let's define a function. We'll just call it fun. Actually, So the function definition is going to be, let's say we're going to give it 10 parameters. Okay. And we're going to say that it's going to take 10 parameters. And I don't know, let's just give it, say, got to do a join of, oh no, we don't, do we need to do that? No, we don't need to do that. We need to do this, and we need to go for each parameter times fun params. Right, so that's the function definition. So what I'm thinking of doing is like creating a, I want to get this to realloc during the function definition so that the values are exactly the same. Okay, so that's going to be, let's say that'll be our function definition. In fact, we can even, let's do this. Let's go 100, no, 1000, 1000 times 1000 plus 100 minus equals. So that's our first program. And what I want to do is force the function that we are about to define to be the right size for, so that when this malloc happens, the function name is the same size, right? So that means if calc, so we can go fun name size. The function name size has to be the length of calc plus the new line plus the null terminator. Okay. So then, if we do that, maybe we don't need so many parameters here. Let's just do. Yeah, we're going to need that. We're going to need whatever the function name is, followed by that, followed by. So this is going to be, I'm just going to call it capital A times fun name size. Okay, so here's what I'm thinking, right? I want this to be run, right? And that's going to allocate a string in the source. So this get line is going to allocate a string of that length, yeah? So whatever that length is, we're calculating it here, should malloc that many bytes, okay? And so once it's malloc that many bytes and then later on it's free, we're reusing that space. What I want to have happen is for my function that I then define in the next one to be exactly the same size as this string, so that when this line of code gets run, define function, read function. So when read function runs, See this X malloc size of. So that's going to alloc some memory somewhere else because it won't be the same size. But this one here, fname malloc string plus. Okay, so +1 includes the null terminator, which we don't need to give it. And then it copies it over. And then it does another malloc afterwards. So that can be just 1 for the new line. Yeah? So getLine seems to allocate 120 bytes when given the null buffer. Okay. Well, we'll have a look at what goes on in the heap when we're doing this, right? So when getLine happens, all right, so our first command, okay, so we're gonna go, what do we got? Process dot send. What's that function that you basically read until and then send? Clone tools? I can never remember. Clone tools. Process. Tubes.process. Recv until end. No, I think it's like I actually want to say without making separate calls. If that makes sense. I know there's a function in here. It's like send after or something. Send raw. Do you know what I'm talking about? Send line. So there's send line, and then there's recv, and there's one that combines it. It's like send a thing after you've received the thing. Is it like send after? Ah, here we go. Send line after. Okay. Send after. Send line after. So what I'm saying is we go send line after, and yeah, it's cool. Hey, so what are we doing here? So it's that in 281. We want to go send line after that, and we'll give it calc. Okay. Now the assumption is going to be that we then send line after we do it again. This time I want to go bun. Does that make sense? Have you got a question? What would happen if you did not free the memory on the line? Well, the problem, Jay, is that I can't not free it. It's completely out of my control. If you didn't free it, it wouldn't be a memory leak. It should be freed outside of the loop rather than inside the loop. So this line here, this line on 297, that should go there. So does that make sense? Because this is doing the allocs and reallocs, and then right at the end when we're done, we should free it. So that's what should happen, and this is the bug, yeah? I learned so many of these hidden gems. Yeah, cool, me too. Like I know there are some that I know, there are some that you guys know, and we can all share those little gems as we go, right? So here's what I'm thinking is like we send that, and then send that, and we'll just spit out everything that we see afterwards. And let's see if that actually gives us something meaningful. All right. Ooh. What happened here? Oh yeah, we've got our breakpoints, of course. So let's have a look. Should probably set a breakpoint on free. Damn autocorrect again. Thanks. Oh. OJ. Yeah, no worries, mate. So that's printf. Okay, so we call getLine. So this would be the second call to getLine. Guest arguments. So what is this? I assume that's a heap pointer. Yeah. Heap. Yeah, so that's a heap pointer. GetLine. Righto. So that's what this pointer here is. So that's now got our, hang on, 1, 2, 3, 4, 5, followed by the new line. Oh, hang on. Yeah, okay. So here's where we should actually end up. Where is it? In our define functions. So where are we? Define function. Where's that actual function that gets alloced? It's in here, isn't it? Here, right? So we want read function, and inside read function, we want to stop at this malloc call here. We want to know if we're going to, what the value of the return of this call to xmalloc happens to be. Okay, so let's quickly squiz through the code. What was that called again? Read function. So disas read function. So there's a call here to xmalloc. So here we go. There's a xmalloc call there, and then strlen and xmalloc. So it's this one here. That's what we want to break on. Now I'm going to take a copy of that and actually put this in here as well. This will be... what was it called again? Read function. Read function. Plus 211. Okay. Now I'm going to copy that. And let's actually do that in here. And continue. Okay, so this call to xmalloc is... we're passing in 1c. So I would assume that that's enough. So what's the return of that? So we've got this pointer here. Now, if we look at x100wx, okay, so there's nothing in there. I was kind of hoping that we would end up with the same pointer that we used to begin with, which I would assume is here. I wanted this to be alloced again. So how much is 1c? How do we print that in decimal? 1c is 1f. 1, 2, 3. Is there an expression evaluator in here? Anyone remember? Prepare to help. Is there an expression evaluator in here? Is it print? Yeah, I know, right? There is a way of getting it to just print it out. Is it in here somewhere? Let's just see if this does. Yeah, it only spits it out in hex. Is it P-X, is it? OX1C. I don't want it to be X. Anyway. What I think we need to do is we need to figure out on our very first call to what's it called? See, now we're attaching here, so we're actually too late. But this is the pointer that we want, right? So, how big is it? X 10W X that minus, I don't know, let's go 10. So 81. Now let me have a think about the way the heap allocator is working. So this needs to, this is the size, right? This is the size of the buffer that was allocated. Am I reading that right? Yeah, so it's right at the start of the heap, which means that's got to have something to do with the size. Oh, okay. Okay, so has this got something to do with the fact that when you are asking for chunks of memory of a certain size or under, you always get the same size? Does that make sense? I got an idea. Okay, so just for testing, let's comment these buggers out. I'm going to go p.sendLine after. All right, so for a test, I'm just going to send A, and we're going to pass in 30. Actually, we'll go hex 30. And when that free is invoked, let's have a look at that amount again. All right. So we want to go, now what is it that we're passing in? We want to go RSP, whatever's at RSP plus 8 dereferenced minus P RSP plus 8. Can we dereference that? Dereference. Do I need to give it a type? How do I do it? Oh, here we go. That was hex PU. Okay, interesting. Thank you, Seska. Okay, so do I have to give this a type? Like this? Ooh. Oh yeah, I don't want to do that, do I? Okay, so I don't need to dereference it. All I want to do is... Yeah, okay. RSP plus 8 is going to give me that. I know I do need to dereference it, don't I? There we go. And then we want to minus hex 10. Okay. So then if we do, let's say 20 of those. Okay, that's more like it. Keep forgetting we're in 64-bit land. Okay, so have a look at this. It's 81. It's still 81. Even though we've specified a size of hex 30. So one would assume that if we ask for the same amount back, it's allocating in chunks. Yeah, it must be, right? Maybe this is why we have like a custom libc or something, because it's got some kind of logic behind the scenes that allocates in chunks. But what I want to be able to do is get this one back the second time, yeah? What's with 2OF81? Hang on. Oh, down here. Yep, don't know. Well, I would assume that this this is referring to... Well, this would be the next block. So this would be a block of memory that's allocated for another use. And this probably points to some other area of memory. Oh, then again, that could just be the size of a malloc. Parody's back. Welcome, dude. Get system doesn't work on Nix. You should know this. That's true. Gotta love these live streams. When you read walkthroughs, always seems like it's a walk in the park. Yeah, man. Well, that's exactly why we do it. Because I always feel like you read a write-up or whatever, and it's like, oh, that's trivial. But getting there, I think, is really hard. Anyway, for one more experiment, let's run it again. But this time we'll set this to like 70. And there you go. So it is definitely allocating the same size chunk every time. So the question is, can we allocate... Like when that's freed, we then want to reallocate a function that ends up in exactly the same location as this, because then we actually have the ability to replace something. West Sound level manager saying. All right, so is everyone understanding what I'm saying? Like there's going to be a malloc that happens behind the scenes in other areas of the code when we define a function, right? The question is, how do we get there? So maybe that's the problem. Oh, hang on. Hang on a second. Right, okay, so when we define, when we do the function thing, when we read the function, yeah, so when we read the function, look, there's a malloc that happens first, right? It's the size of this funcdef. Okay, so this funcdef, how big is that? Aha. Okay. All right, so just bear with me for a minute. Okay, so we know that like we're getting chunks of certain sizes, yeah? So, oh, hang on, I've messed something up. Disas read function. Where's that other malloc call? So there's two malloc calls in here, right? Where is it? Put s, exit, x malloc. Here we go. So 183 is the other one. So let's do 183 and 211. 183. Okay. So what we'll do is we'll start with this, and then we'll just do a very basic function definition straight afterwards. And for now, I'll just, I don't know, we'll call it 4Bs. And we'll go like that, just so that it's a valid command. Okay, we'll just go with that. Now the reason why I'm doing this is because I want to see whether or not the actual op, so this func definition, when that gets allocated, do we end up with that being pointed to by by the input buffer? So the input buffer we know is going to be the first buffer that's returned from the heap because it's the first thing that's mallocked in this whole program. So I'm hoping that the function definition, when we malloc it inside our read function is going to return a pointer to the exact same location that has just been freed. Okay? That's my thinking. Okay. So we'll make sure that's written, and let's do the exploit thing. Okay, so again, free. Free is, so this is the address that we're freeing. Take a copy of that. Let's continue. Get line. Call xmalloc. Okay, so this is the first xmalloc call, yeah? Based on what we're seeing here. Where is it? This xmalloc here, right? So size of funcdef_t, which is, that's a pointer, so 8. That's a pointer, so 8. Size t, that's probably 8 as well. So 24 bytes. And what's the size? 24 bytes. Okay. So what is it going to return? This. Why is that different to... Oh, it's the same. Oh! Okay, here we go. So that means that our function definition now sits in exactly the same spot. Right? Now, okay. This is exciting. This is exciting. So we have a name. We have a pointer to a bunch of operations, and an op count. Okay. Did I just come back to an... Yes, you did. So I think, based on what we're seeing here, is we have just been allocated the same chunk by defining a function in the second call because our xmalloc has allocated memory in this spot. Okay, so then when we malloc here, what do we get next? B0. So x20qx. Right. This is interesting. Not sure what this points to, if anything, whether it's just size. I don't think that points anywhere. 20f41. Yeah, there's no memory mapped in that space. So it's got to be a size thing. Maybe there's been some other malloc call behind the scenes. Did it reset the memory from the first xmalloc? No, it didn't. This is the second chunk. So the other one is still... Oh, maybe it did. Oh, hang on. Minus... Ah. Is that the address that we thought it was? Let me just check. I'm second guessing myself now. Where is it? Here. Yeah, it was here, right? Yeah, I probably do, hey. Yeah, it's that. Okay, so it's definitely that. So maybe it did clear it. But it does look different, doesn't it? Because according to this, the size is only 21. Are we missing something like dumb? We just had another follower. Extreme Co, thank you for the follow. And Razor Sazo, I missed you. My apologies. Maybe it's because a realloc has happened. I know reallocs only happen when we define a function that is exactly the same name as one that we've already defined. What's clear though, what's very clear at this stage, is that we have the ability to overwrite this. So yeah, that's rounded up to what's clearly D-word alignment. So where are we at? We've just allocated the second block of memory. So xmalloc. So we allocated that, and then we allocated whatever this was. The function name. What function did we gave it 4 bytes, didn't we? That's the string length. Oh no, it's not. So xmalloc racks. So this is what's just been allocated. So I'm just going back to where we were, minus 10 hex. So yeah, that is significantly smaller. Why is this not 81? That's what I'd like to know. Either way, we know that... Maybe it's the get line that does it. Maybe that's what's doing it. It's always doing the first one at 80. This is really interesting though. And the reason for that is, like, if we can continually reuse chunks of this memory, then at the end we can kind of overwrite this again with a bunch of stuff. There's no reason that we can't do that, right? So, yeah. So we... Yeah, I think that's what's going to happen. Okay. Let's just quickly check something. I'm just going to remove the automation for this just for a minute. Let's go break on malloc and run. Okay, so new. Let's just let it do its wiring thing. Actually, let's go break get line. Okay, and we want to step into get line and then break on malloc and continue. Okay, so where are the parameters for this? I think racks, sorry, is it RDI? Which one is it that you pass in? I think it's this one here. And as a result, that's going to round up to 8. Yeah, okay. So get line. What's going on here? Oh, this is inside lib ret. Here we go. So, hey, there it is there, right? Looks like get delim is what calls... Well, actually, maybe not. I can get out of this. Yeah, okay. Right, so it looks to me like getLine is actually forcibly doing that 80 byte buffer to begin with, right? So if that's the case, then if we've got like up to 80 characters or whatever it is to start with, minimum. We could... I can see the path unfolding. I've just got to articulate my words around it. We need to... What do we need to do? I think... Yeah. Have I lost anyone? Everyone's still with me? I kind of feel like I'm alone in my own head. We clearly have the... Yeah, I know, right? So here's the go. We have the ability... We know that there's going to be like hex 80 bytes allocated up front. That's what the getLine malloc invokes, yeah? So we go through our first line of input, whatever that happens to be, even if it's not function related or anything like that, we then end up freeing that buffer in the free. Then when getLine is called again, it still writes to that same location. The difference is that when we're parsing that, we're parsing the location that we have just freed while still using it as an area of memory that's being allocated by the allocator. So, what I want to know at this point is this. So if we pass in let's do this again just to make it a bit... Oh no, we don't need to do that. We don't need to make it longer. So we don't need to worry about the size at this stage. We know that we've got hex 80, right? The second thing that we're going to send in is... we want to define a function. We want to define a function with a name. And then that function definition, like the actual pointers to those components of the function, is funcdef. We need that It's coming. The words are coming. That's a pointer to a name. we want what we would actually like to be able to do is we want to overwrite this with, sorry, I'm trying really hard to think. Aha. Okay, so if we define a function in our first payload, right, then inside here, in this global thing, in BSS, we are going to write the definition of a function. Hey, insolent fool. Okay, here we go, here we go. It's happening, it's happening. We are storing pointers to the heap in here. If we can change, we obviously know the address of this because like, all right, so there's no PIE in this, which means BSS is going to be in the same spot. Info var function definitions. I want the address of this. Aha! Is that? Okay, so we know there's going to be heap pointers in here, yeah? All right, okay. Just hold your horses. Looks like there's a check for the number of functions. Yeah, so here's what I'm thinking. Up front, this first payload, I'm going to change it. Let's funcdef equals. So we need to define a function by a name. So let's just call it A, uppercase A, because we know when we see that. Function def A, and we'll give it 5 parameters, 2, 3, 4, 5. Okay. 2, 3, 4. I actually want to see if we can, like in the code, because the name, if we can overwrite in our next loop, if we can overwrite this with a pointer to that location, then that's going to give us the ability to leak a heap address, right? And so if we can leak a heap address, then obviously we can figure out where our own payloads are in memory. We can figure out where our strings are in memory, which is clearly going to be important. So if we know where we are in memory, we would either need a buffer overflow or the ability to like attack the heap metadata when we're doing our thing, or I don't know, is there a means for us to do like a write what we're using this mechanism? Can we, because if we can convert what we have into the ability to write to an address, then I mean we know oh no, we don't. Well, we know what the libc version is, but we don't know where libc is in memory. So we need to figure out where libc is going to be. So To figure out where libc is going to be, we would need to leak a pointer out of the got, and there's no rel row either. Yep, no rel row. Okay, so the got's in the same location. PIE is disabled. Got's in the same location. We can write to the got. We can read from the got. So that means we can actually, if we have the ability to abuse what we've just discovered here, if we can overwrite our function definition with, so we define a function. We define a function, then we take the next round of input. When we do that, we overwrite the function definition with something we control. So we could change this pointer. If we change that pointer, that does a string compare, it does free. Can we spit it out somewhere? And copy after mallocing. Oh! Aha! Ahahaha! Hang on a minute. Right, so we would need to modify the operation that's associated with a function to make it think that it's a function, causing it to write out the name for the... Oh, hang on a minute. Okay, so... Okay. It's a little bit confusing, right? Yeah, it prints the name containing the leaked address. That's kind of where I'm going. So here's what I'm thinking, right? Let's just do a couple of function definitions side by side, okay? Just so that we can fill the table out a little bit. Yeah, actually, hang on. Let's do this. Dot format C for C in A, B, C, D. There you go. So that's 4. Function definition. So we want to join that together with a yeah, space dot join. Okay, so that defines a bunch of functions. Then I want to define another function. So let's get rid of all this noise. Okay, so the first thing we're going to do is define a bunch of functions. Func defs. We'll call it defs, given that it's doing more than one. Okay, so we define some functions. And then what I want to do is define a new function. What is it going to do? Let's go with... We'll just leave that as is. Maybe we'll do a few more. We won't call this B's. What are we up to? So A, B, C, D. Yeah, let's do a bunch of E's. And just see what that does. Because my feeling is that when we define that, like, so immediately after we've done this, the assumption is that our function definition for this E function lives at the start of the memory region that this payload here, this line, gets allocated to, so that when we free it, it doesn't break. So then after that, so we just basically want to get past this second free, right? Let's see how that goes. Okay, so here we go. All right, so xmalloc is being called here, and we're passing in 18. So this is the call that we're expecting to return for this. So x20x blah minus 10. Okay, so I'm assuming this is where that other shit got allocated to first, right? We didn't even check that. So, and then we go string length. We malloc again. This time we get back B0. So we've got 90 B0. Obviously we're right next to each other. So our currently, according to the source, we've done that. Now we're going to copy the string into here. So I would assume we're going to see after the string copy, we've got another followed. Oh, it's a sub. Ah, oh, B-Man, you gifting subs again, dude. Thanks, man. You're a legend. Okay, so aha. Okay. Ah. Yes. Just a minute. I'm going to stop that. Cancel that. Let's go back over here. Now I'm going to stop this here. Yeah, I don't want either of those. Let's just take those out for a minute, because all of these read function calls are reading in the A's and the B's and the C's and all that sort of stuff. Breadstick, hello. Yes, I think we are. It's proving to be a challenge, but I'm not gonna lie, I'm really enjoying it. Okay, so here we go. So free, we are freeing this. Let's go back to our little helper doohickey, which I seem to have lost in the noise. And as we all know, it's faster to just keep tapping up until we find what we're looking for than typing it out. There it is. All right, so we can see, like if we go XS, that's not what I meant. Yeah, okay. See all the zeros that have been inserted here? These are the nulls from the tokenizer. So you can see that it is tokenizing behind the scenes, yeah? So 2D, that is that first piece of input that we put in here with all of this stuff in it. Okay, so we've got a bunch of functions sitting there ready to go. Yeah, I think it's going to be late tonight, Atwolf. I'm feeling the vibe at the moment. It's a bit of fun. Okay, so now what I want to do is we want to break here. Okay, so let's run. That's going to break a get line. Get line's not going to realloc. Okay, so xmalloc. This is where we are now creating another function of the same size. I would expect us to get the same memory address back as what we were looking at before. And I could be wrong. QX Is that what we were looking at before? 2010. No, it's not. Why is it not? Is it because it's too small? I wonder if it's because it's too small. Maybe we need to make it bigger. Nah, man, I reckon it's size. That's my current feeling. So we know. Okay, so we should be able to just like, hang on. So they're the function definitions. Let's go with final func is going to be that thing. Oop. Okay, so here I want to give it final func. And we're going to try and force it to be the same size. Okay, so if we went final func and we want to, I want to fill it up. I want to, hang on a second. No, that's not what I'm thinking. Okay, wait up. So every single operation because clearly we're doing a lot more mallocs now because we're allocating for every function definition we're doing. We're allocating for every name that's associated with it, and then we're allocating yeah, that's kind of what I'm thinking. I'm pretty sure it's a size related thing, right? So if we just did something like pad it out. So we went, I don't know, let's go, well, we'll use spaces. We should just use spaces, right? Because spaces are effectively NOPs. That times so we know that's the size that we want. We want subtract the length of final func, and maybe take a couple off in case there's like extra nulls or some shit. So I just want to kind of fill it out so that it's the same size. Does that make sense? Let's give that a go. Let's just see what happens. All right, so free. We are, this is the address, right? X 10QX blah minus. I like to do the minus because it shows us the allocation as well. Okay, so we can see that's where we should be allocated. Now, if we continue, actually that's gone through the process once already. So now, oops, where's my cursor gone? There we go. Now I want to break at this location. And continue. Okay, so get line should do nothing. Oh! What'd I do? That's not what I was expecting. I'm not gonna lie. X, 10x. I don't know why, but I find this really fun. And it's ridiculous, isn't it? It's like 10:15. Been doing this for 2 hours, 15 minutes. I've barely made any progress, but I'm thoroughly enjoying myself. Okay, so we get to get line. Now I want to break at the read. Why is that happening? Okay, so let's just stop for 1 second and reevaluate. Let's get rid of this. Because this is what we did before, right? This is exactly what we did before. We get to here, break, and we hit the break point. Why is that? Why is it that appending those spaces results in that behavior? Is it? Do I need to, like, do I need to put the spaces before? Is that? Final funk. Like, is that going to make a difference? No. I've had lunch with him a couple of times, definitely. Thanks, Parody. You'd be on my side, my friend. Maybe it's too big. Maybe I've done something dumb in my calculation. So let's do, I don't know, let's do that. So we've got a bunch of spaces. Does that even make sense? Oh no, why do I need a Docker container? Yeah. Thanks libc. And it was crashing on my host. So yeah, I don't know what was going on there. Aha! Okay, so that behaved differently there, but we're still not getting the same pointer as we did before when we called free. Because that was 2580.010 and we're getting 2580.310. Yeah. Need lunch now. Thanks, Rasta! All good, man. You go do your thing and you enjoy the rest of your day. Thanks for dropping in and for supporting as always, my friend. Yeah, we're playing in the heap at the moment. What I'm trying to do at the moment is force the allocator to give us back the piece of the puzzle that we were getting before. Maybe I'm getting ahead of myself. So let's quickly go back to this for a minute. Let's not do these function definitions. Okay. Instead, we will do what we did before. And I will just define a large amount of work. 10,000, 10,000 plus 10,000 plus 10,000 plus 10,000 plus equals. Okay, so we have that. Now what I want to make sure of is that we are getting the same thing back when we do this. So, but this time I'm going to make sure that it's kind of in line with what we would expect. Does that make sense? All right, so we are freeing F010. Continue. We're up to get line. I've cleared my clipboard, so let's break again on this xmalloc. And that broke. Not doing that at the moment. We're doing a PicoCTF 2018 challenge that hasn't been solved much. So maybe I need to get, maybe it's this. Although that wouldn't make a lot of sense, would it? You know what? Let's just do this. Final. I reckon there's something strange going on with these things that I'm doing, that I'm over confusing myself. Okay. So that is 36010. Right. 36090 is what's just come back. Yeah. Let's just quickly validate that. Here we go, look. 010 is what was being passed in, size 78. And here, xmalloc returned 090, and we wanted 010. So why is that? Why is that? Does that mean that those things, like it's actually been allocated for other reasons? Well, I'm out of here if it's not that. The only thing I know about is fast spins. Ha! I'm pretty sure that it's going to be related to that for sure. My guess at this stage, based on what I'm seeing here, is that we just need to make sure that we can convince this thing to cough up the pointer to the freed buffer when we try and create this function definition. But I'm really not sure why. In fact, I'm going to undo all this crap for a minute. This is the beauty of Vim. Before I did that ridiculous joining stuff. Aha. Is that where we got to? Oops. Clearly that's not what it was. Yeah, I think this might have been it. So we send we've got a function definition So we send, I think we send that, and then we just ignore that. Yeah, let's just give this a go. Out of ideas. All good, man. We'll get to it. I'm pretty certain that we'll find the solution to this. I'm feeling quite confident. Okay, so we're freeing up 7010. Hey, Smash! Good to see you. Oh, Wilbur's in. I didn't even see your name, Wilbur. Okay, so if we go back to this. Okay, I don't need to because it's already there. Get line, xmalloc. Okay, so we aren't seeing the same come back. All right, let me just check something. So get line was caught with this. So X. Let's go 40 QX this. Yeah, okay. So we can see this has definitely been, it's been reallocated. At the point that get line is called, I'm assuming that this is going to be marked differently because it would have been freed. So yeah, we can see that was allocated all the way up to here. There's a pointer to the next chunk, which starts there. Yeah, so that's been freed. What got this? What was it that got this piece? How do we see this before? I could have sworn we got the same pointer back. Could have sworn we managed to get the same pointer back, didn't we? Gather. Yeah, I know what kind of bug it is. It's like a double free, use after free. So the call to get line happens and something's allocated. And then a free is called on that, and then get line is reused, assuming that the value, the buffer that we've passed in is still legit, which it's not. It can still write to that buffer, but it's not actually allocated. And then after that, we want to be able to allocate that buffer to something else, which is what we're currently playing with. So I kind of want to define a function fun name size. I don't need any of that, do I? That's right, I got rid of this because we don't need any of that shit. And then we just need to define Yeah, it is a spot of fun. Pardon the very, very lame recap, but my head is in a completely different space at the moment. And I just want to focus on that for a sec. 4, 5. Okay, let's just see what this does. Okay, free. Get line. Malloc. Right, so that's still returning. Maybe. How big isn't? I think we're going to have to pre-allocate functions. I can't remember how we got the same pointer back in our previous call. Oh, hang on, maybe it doesn't matter. Oh, it does matter because free is going to be called with that same pointer again. Yes, so it does matter. We need to get that pointer reallocated. So if we're going to get that reallocated, we have to make use of xmalloc calls. Okay, so this stack element's too small, so that's not what we want. It's really these, isn't it? So funcdef-t, which we know is small. Need to make ourselves. Ah! I may have just had an epiphany. Maybe this isn't what we want. We need this here to be the same size. So how big is an operation? An operation is 16 bytes? We can figure that out in just a sec. So if we malloc, then we do a calculation after we string copy. If we shift left by 4, what are we multiplying by? Hang on. P Rex. $50. So we go from so we times by 16. So each thing is 16. So if we go with print 80, hex 80 over 16, we get 8. So that means we basically need 7 operations. Okay. So if we make this have 7 ops, then the second allocation for the operations should end up in the first spot. Yeah? Let's try that. Righto, so X malloc. Okay, so we know that's not going to... Oh no, phew, that's a relief. Okay, so that allocates and we get 0B. It's this malloc here after the string copy. I'm hoping this is going to return a pointer. Aha, there it is. Okay. Okay, so it's the operations that returns the same pointer. X, 20x. Woohoo! Okay, that makes sense. Ooh, did someone cheer? I got some bits. Woohoo! Okay, that makes sense to me now. I am down with that. Okay, so that means our operations lie over the top. So what we now need, we need to provide input, which kind of makes it look like operations that are going to leak. Oh, yes, progress. This is making way more sense. Way more sense. Okay, so we need to, we want to say leak an address. Yeah? 0, 1, 2, 3, 4, 5, 6, 7. What do we want to do?
I wished upon a star last night and thought of you, but it must have been a dream 'cause you're not here. I've never been one to believe in fairy tales or fantasy.
We have the ability now to define our own set operations by providing another series of input, yeah? But before we quickly rush off and do that, let's just... Oof. Not enough function arguments. Oh. Really? What did I do? 1, 2, 3, 5, 6. Oh no, that's right. So we define that function. Op string was null. So does this mean then, like, if we do, if we read this input in, then we should be basically splatting that gives us, what does it give us? What does it give us? Did one of the tokenization boundaries end up in the wrong spot? Line 150. Sorry, I was just in a world of my own there. 150. No, I think... Maybe what we need to do. 151. Yeah. Let me just think about this for a sec. We kind of want our function definition outside of where the tokenizer. Ah, it's so confusing. Yeah, okay. Alright, so we should be getting back 7010. Which is actually 259. That's kind of where I want the malloc thing to be, so I'm going to get rid of that. Put 259 there for future shenanigans. Okay. So here we can see, just look at, okay, op count equals farg. Farg is what? Oh, that's what's read out of, yeah, here. So 7. Farg is 7, op count is 7. And then it's trying to tokenize. Oh, do I need another space? Is that my problem? Is that what you were saying? So I need a space at the end. Like that. Maybe that's it. So we're definitely getting that address back, so that's a win. If we continue now, what do we get here? Invalid operation. Not enough. Okay, so invalid operation is a different thing. Invalid operation. Op string is blank. Ah, that's because it's done the next read, right? Is that right? Oops. Invalid. Okay, so this is parsing more ops. Okay, so kind of looks like only way our message would occur. Yeah, I hear you, man. So we got through here because I can't remember where enums start. Did they start at 1 or 0? Yeah, they do start at 0, don't they? So that should be 0. 1, 2, 3, 4, 5, 6, 7. Okay, so let's have a think. I'm wondering, going back to my previous thoughts, I'm wondering if like we need to justify, like, to move our function definition away from, no. Let's just see what happens when we do this. Malloc. Ooh. Ah, okay, so we were trying to, okay, I see what's going on there. Okay, so that line is causing breakage, so I can't do that at this stage. We do need, I think we need to, we've got to stop it from dying at this point, right? Yeah, okay, so invalid operation blank, which makes perfect sense because I'm kind of wondering if we should yeah, I reckon that we need to munge this line here to stop it from shitting itself, but I don't really know what that is. Maybe we just need to move this input. No, but why would that be the case? Because what this is saying is matches a function definition. Oh, hang on, there's two spots where this happens. 3 spots? 1, 2 spots. So which one is it? I reckon it's run op. Okay, so if we go back here, let's do this. Actually, 7. I'm using 7. Okay, so when I get here, I want to break at run op. Okay, so it's not run op that's causing it, which means it's inside pars op. Matches function. Okay, hang on. Aha, okay, so we do get in here. Yeah. Okay, I think it's becoming clear. So we want to get to that xmalloc, and then let's go break pars op. Okay, so what is it doing here? It's tokenizing the number of ops, right? Hang on, while result pars op. So pars op, we should end up with an add, right? So okay, Okay, so we try and read that out and it comes out at 0. So then it's going to say, let's do a string compare. And we're comparing against plus, and is it the same? Yes, it is. At which point we set that local variable to 1. Oh, sorry, the pointer on the heap to 1. So going back here, add is 1. And that answers the question. That's definitely 0. So that just helps clarify. 0-based enumeration. I'm pretty sure I'm doing 7. You got me second guessing now. Anyway, let's continue, because this should leave, come back in. Racks 7. Jump. str toc. Parse op again. Yep. So we can go. How do I clear the breakpoints again? That's what I want. Alright, so this is going to do the same thing. Compare to plus. Ooh. Well, well, well. Isn't that interesting? Yes, 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 yes. Knew it, knew it. I'm gonna fill this up with spaces. I'm gonna justify that to the left. Let's just pad it out with like, I don't know, 50. Okay, so remember, as we're filling in the operations, we're overwriting the thing that we're parsing. And that's mucking with the input buffer, which is what I think is causing the problem. Oops. Does that make sense? Invalid operation plus. Really? Is it not big enough? It's a different error, so maybe it's not big enough. Hang on a minute. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19. So let's go OX80 minus 19. Does that seem reasonable? Aha! Ha ha ha! There we go. So our second call to free doesn't break. Boom. Okay, so we have the ability now. That's actually really good progress. I'm pretty happy about that. But what we need to do now is we need to abuse the fact that our input buffer is sitting over the top of those operations. So what operations can we get this function, which we've just defined, which is A, is that what we called it? A. What can we do with this function definition to get it to... Okay. It was good enough when you did it before, RFC. Alright, so in memory, let's just quickly go back to here. Let's go. This always reminds me of Beat Saber, this song. Yeah, okay. So these are all the spaces that we filled in. This is the operations that it splattered over the top. Right. Phew. This is really quite cool and quirky. I can understand why so few people solved it. Okay, so if that's the case, we have the ability to now overwrite all of these operations with our own stuff. So that being said, what can we do? What are you guys thinking? We need to... Equals does a printf, yeah. So I know we're going to need to do an equals for sure. Which is a what? 0, 1, 2, 3, 4, 5, 6, 7. Ah. We need to... Okay, here's what I'm going to do. Let's go back to what we had before. We're going to go P... What is it called? Functions? Flavor func... Yeah. So that there is the first function that we have actually defined, right? And that points to the heap. So the address of functions... Right, so here's what we're going to do. So ADR functions equals... Oops. What a great song. So once we've done that, I'm pretty certain what we need to do is just p.sendLineAfter. Oh, we're going to have to generate some shit here. So this is going to be operations. So we'll call it ops. So our ops is going to be... We're going to start with... Oh, it's This Is Not OJ. Nice to see you, dude. So we're going to treat the very first thing... Oh. Oh, no. No, that's okay. We want to define, we want the first operation that we're going to run to look like. Okay, so hang on. Let's make sure we do this nice and clearly. Op function is 7, right? Zero, 1, 2, 3, 4, 5, 6, 7. Function definition. Op. Let's go. Func def is 7. Op func is 6. Now this is important, right? Because what I'm thinking here is that when we go function names are the same. Hang on, where are we? Righto, so when we run our operations, see what I want to do is say I want to invoke this and I want fval to be a pointer, and that pointer I want that to point to the heap. Is fval. Remember that comes out as a function definition. And then the function definition, so the first value in that function definition is a string. It's interpreted as a string. So we want fname to be the address oh man, this is doing my head in. We need it to be the address of something that contains why is this so painful? You can see where... Yeah, I think so. I'm pretty sure that we can get this to be invoked, though. The question is, how do we control this? So, for function, we need to pass in... Sorry. So that defines a function. Ah! not quite smash. So to recap, if we just go to main, I'll show you what I mean. Get line mallocs hex 80 bytes to begin with. Okay. Then what happens is down here, this line gets freed. The same line that was mallocked in here gets freed. Okay. Then this gets called again, and get line doesn't realloc because this is not null. So it writes over the top of a buffer that's been freed. And then when we go through all this process, we get down here again, and then when free gets called again, it breaks because it's been double freed. So what we do here, when we go call getLine, we run through here, and when we call getLine again, we need to pass in some commands that cause operation parsing to reallocate the same pointer that is used here, so that when the next call to free gets invoked, it doesn't fail. At that point, we have the ability to run this again, and once we run it again, we can overwrite all of the function operations, so operations associated with a function. What's going on? So you'll see a function definition has a number of operations, right? And so when we create a function definition, you'll see here we malloc however many we need, operations based on how many we've said. And so what we're doing is that we are making sure that at this point we allocate the same size buffer so that the operations buffer overlaps with the buffer that we're writing the input to, at which point our next read into the input buffer will overwrite all of those ops. Okay, so then what we need to be able to do is, oh shit, we're gonna have to repeat this. Which means okay, that means that we're going to have to, rather than do this calc thing at the start, we are going to have to define another function. And I'm going to make it basically the same as this. Oops. I'm going to make it do that. And this one's going to be uppercase A. Because then we've got two functions that we've defined. Oh man, it's bending my mind. Does feel pretty awkward, but I'm confident that we're going to get there. I really am. But what I just need to figure out is for this next round, when we've defined this capital A function, it's going to point to the operations that we're about to overwrite, yeah? And so now we need to define those operations that go over the top. So what are we going to do there? We are going to, I think. Here's what I'm going to do, right? I'm going to do this. I'm going to reallocate. So the reason why I'm doing this is because we need to force another malloc so that our input works again, right? I can't take any more, Captain. Need sleeps. Thanks, mate. It's been super good having you on. Appreciate the support as always. All right, so I want to do that. That redefines this first function, and in doing so, we call realloc. Oh, hang on. Only if the op count's different. Okay, so that needs to be 8. Okay, so that needs to be 8. So that'll cause a realloc, and the realloc will then give us the input buffer back again, right? Yeah. Okay, so once I've got that, we actually then want to invoke. Oh, man. This is just so that we know we can do another round of inputs if we need to. But what we obviously need to do as soon as we've done that is we actually need to call the function that we've defined. Okay? Which means we need to invoke A. Oh. If we invoke our A-defined function, what do we have to give it? We have to give it... Oh, this is where we're actually splatting over the top of... Ah, okay. So we need to make sure that we align what we've done. Ooh. How big is that? 1, 2, 3, 4, 5, 6. Okay, so we need to basically fill this out with we need to oh Christ. Okay, so we need to go this. We need to fill this out basically with zeros until it fills up the first of the, like, to get to the point where the first operation is, right? So if we look again at our function definition, our operations, we've got, so if we fill it with zeros, then that becomes a constant. I don't know how. Okay, so we want to align this to however many. Hang on. We want to do whatever the string is, the length of that. Okay, hang on, let's just go x equals that. We want the length of x over, I would assume hex 10. I know we want the remainder when divided by, don't we? We want the modulus. Yeah, we want both. So basically we want the length of x subtracted from that, which gives us, that's how many we need. Yep. Because we want to align this to the ops. So that's going to be the length of the ops mod that, and then that's how many of these things we want. So, oops. Oh, hang on. I don't need to do that. Oh yeah, I do. No, I don't. I've just overthought this massively. We should be able to just do that. So that will force us to now be in a line. Oh, no, hang on. It needs to be 2. Yeah, it needs to be 2, which is what I did. Because we need to make sure that we align it for each operation. Yeah. Yeah, exactly. So I need to make sure that that happens repeatedly so that we reallocate to get the memory back. And then we also invoke the function that we've just defined here that contains the operations that we are just about to write, which include a heap pointer, which is which is what? Yeah, bugger. Let's just comment that out for a sec, and comment that out for a sec. We define the function get line. So that's going to return F010. Yeah. Is that what I want? Yeah, I think I am. I'm confident that I'm going to be able to solve this. There's enough of the picture being drawn in my head slowly. So what did I do the first time? Okay, so that is the second. Where is this? Let's have a look at the content of this. Okay, so there's definitely heap pointers in here, pointing to the individual functions. Right, so if that points to this points to somewhere in the heap. What's in the heap? It's a heap pointer. Cool. Okay, so that means if I define a function, so that means at this point, yeah, I think what I need to do now is redefine that to get that pointer back. And then here we need to go, okay, we're gonna define, do we need to define a function? PicoCTF. So as we're parsing, let's see what happens when I just call function. Yeah, okay. Alright, that's what I'm going to do. I'm going to make that op func. So we're going to just invoke the function. And I'm going to go pwn p64 addr functions. And the question is, do I need to pad out the rest of this so that we fill out all of the ops? So like, oops. And how many times do I need to do this? Or maybe I just need to do nops, don't I? Is that what I need to do? How many do we define? 7. Where's a nop? Nop. Case nop. 0, 1, 2, 3, 4, 5. Op. Nop. 5. Okay, so now how many times do I need to do this? I said there were going to be 7 ops. This is taking up 2, 3. Now I would assume I also need to do pwn.p64 of the whatever the nop, like everything has a parameter associated with it. So we would need to do this. Whew. Keep your heap leaked. Yeah, so like 5. Is it 5? See you, Binchuk. So that's yeah, because each one is only 2 pointers, right? But they're all okay. So 1, 2. Yeah, that's 1, 2. 3. So there needs to be 4 of those. Oh well, let's see what happens. I'm getting there. Getting there. Okay, there we go. So that's our second. Okay, let's see what this is doing. So, free, read again, get line. Here we go, we're going to do our string tokenization. What we should do, actually, we know this is the heat pointer, so let's do another 40QX from here. Let's just see if it's done what we want it to do. Excuse me. Okay, so yeah, we can see. Oh, hang on. Yeah, 6 5 5 5 5 0. Okay, yep, that's good. Okay, so that means hopefully if things go to plan, when we start parsing the op as per right, so we call parse op down here. Let's see what happens here. We need to make sure that that actually functions as expected. So we'll have to go into this. Okay, so it calls scanf and should return 0, at which point... okay, so it should be redefining a function now, yeah? Because that's what this is. Yeah. So that's going to cause the realloc, which should hopefully... Okay, so string compare. String compare again, this time with... It's going to be the last case. Okay, slash equals... hash, which is a not. String compare, function definition. Here we go. Read function. Called string tokenize. Okay, so it's reading out going to do the scanf thing again, read out the value of 8 and store that value. Okay, so xmalloc, we're calling malloc for 18, and that should return crazy area of memory. And then the next, so we've got string length, which is of 1, so we call malloc for that. We then call string copy, and then xmalloc here should, there you go. Is it doing, yes, 80. So we should get that first one back. Oh, don't think that's right. I'm pretty sure that's wrong. EA010. We've got EA 1D0. Which is a bit upsetting. Because that's not pointing back to the buffer that is going to continue to be used in main. Okay, we'll come to that in just a minute. Let's see if it actually executes the operations that we've given it. Okay, so that's just doing the classic tokenization with all the pluses. So I'm just going to keep as going all the way down until we reach. I know that's not going to be pleasant to watch, sorry. But I'm just watching like RCX to the point where it should drop down to having a plus followed by an A. There it is. And then very soon, once we've finished parsing all of those operations out, we should get to parse op. Okay, so here now we're calling parse op again. We're going to end up here looking through the functions. Okay, so we'll step into that. And then try and read, which it doesn't work, and then it's going to do a bunch of string compares. What happened there? Did I just bail straight over the top of it? No. Yes. I did, didn't I? Oh no, called read function. I've messed something up, I think. Ah, here we go, run op. Okay, so let's go into run op. Yep, parse op. Okay, so run op. We should end up in a case where we've got our array of operations. Now, where is that? Is that what Rax is? Or RDI? RDI and Rax are the same thing. RSI. None of these are pointing to the heap. So right now we've hit 7 and it's saying call function. Where are we? We're in run op. It says define a function. Ah, okay, of course. Of course. So it is defining the function that we have just invoked here. Okay, that makes a bit more sense. So defining the function here, that will have done the realloc. Okay, that makes more sense. At which point, if we look at this, maybe that's been reallocated now. I should probably have not stepped over that. I think maybe that's what got pulled out. We'll see. Okay, so Here we go. This is it. It's going to invoke our function now. It's calling parseOp. ParseOp again. We're going to end up with this. It's going to search for the function based on our definition. Pretty confusing, eh? So we'll step into that one. Scanf will fail. It's not going to find anything there. It's not going to find star, minus. I might need to change the playlist. We've listened to these songs on loop for a while, haven't we? Let's go with something a bit different. It really is a horrible calculator, I agree. String compare equals. Okay, NOP. Function definition, nope. Righto, so this is where we're starting to look for function definitions. And we can see that there's that one with lowercase a, which is about to compare. And that will fail. And then it's going to loop to the next one. And this should match. Which it does. Alright. So that's going to return a pointer. And then leave. Alright. We're calling runOp. Oh, look at that. Ha, it's pointing to the thing. It's pointing to the thing. Yeah. It's pointing to exactly the thing that we want it to point to. From what I can tell, because our op is here. Right, so when we go, see how we copy the value out onto the stack and we say run it. So we call runOp. And this op is saying, what are you? Which based on switch statement is saying running. Okay, running A. So this is going to spit out the fact that we're running our A function, which is exactly what we want because we want it to be running our A function. Where are we? Just trying to figure out what this stuff is pointing to. Jeez, what are we passing in now? It's calling runOp. RunOp with an operation pointer and a stack pointer. So that's interesting. Whew. Man, this is doing my head in. Invalid operation. Does that fail when it's an invalid op? Yeah, it does. Yeah, I know. It's like it's off kilter for some reason, isn't it? Why? Yeah, let's just see what happens, because there's probably more ops to run. So that's okay, as long as it does it again, right? Here we go. Okay, so that's okay. So hang on. Invalid. Okay, so as long as the op is invalid, it's fine. See, Wolf. Okay, so I don't know what the value is that we've spat out, but there's something going on there. So no, that's not going to work, is it? X int. Yeah, okay. That's the tokenized input that we've seen, so that's fine. Step into this one, and hopefully we'll very soon we'll see the ops that we actually want it to run. Invalid operation plus. That's okay, we can deal with that. This is fine. As long as we end up invalid operation again. Right, so we're slowly working our way through those heap addresses, yeah? Because it's running A. Or it thinks it is. Ooh. That's a little bit different. At least we're coughing some stuff up. Okay, so ooh. What did that actually do? So Rax is 5. So this is effectively the NOP, yeah? Yeah, it's the NOP. So we must have done... Hang on, what is this? What is this? Doesn't really look like an address though, does it? Like, what are our heap addresses at the moment? Oh, hang on. EAB0. Ooh, looks heapy, doesn't it? It looks kind of heapy to me. So if we had this and we go .r just 8 wide nulls. Let's import perm. Go po.u64. Whatever this is. Maybe I need to L-just that. EA0B0. Oh, hang on. Hang on. Ah, there's spaces in here. Is there? I think there might be a space in there. Yeah. I'm excited. So here's what I'm thinking. Once we've sent that, we can just go p dot recv until. Now we're gonna read running something. Okay. That gets us to here. Then we want to skip all this other invalid shit and come to here again. Right? So we want to do it again. Then we want to go recv line. So that's going to give us whatever comes after running. It's going to include a new line. So we basically want to chomp off like the very last character to get rid of the new line, right? Okay, so that's going to give us the bytes that represent the address that's happy to actually spit out. Then we need to do the, oops. So that gets us to exactly the same point we're at here. So we need to do this. So we L just 8, pad it out with null bytes. Okay, so then we get our full thing, and then we can go pwn dot unpack 64. Okay, so that's going to give us what we believe to be a heap address. So then we can go print heap address is hex heap address. Fly like the wind, bullseye. Oops. Oh, I need a 1 in there, don't I? Woo! I'm excited. Is that a heap address? Yes! We have a heap address. Yeah, basically. Basically, I think that's a fair summary, Smash. So now we need to do the same thing, but this time I think with with the GOT. What's the how do you view the GOT in PETA? I know Gef has like you can type GOT and it's just there. What's the really easy way? GDB PETA show GOT. How do I do that? Because I know Gef does it, right? Anyone? Anyone? Show global offset table. Show me the money. How do we... I just want it to show me the things. It's got to be a really nice way. Like just saying, can you please? Oh, I've just used Peta for so long. I should really play with Geth a lot more. Come on, really? There has to be a super easy way of just saying, show me the god. Show me the god. Come on. Yeah, I have used it in previous streams. Python print header dot. Show me the god. This looks old. Alright, let's do it the other way. Let's do it the old-fashioned way. Disas main. Called free, right? Info function str. No, let's go. Okay, so the GOT does start at free. Let's have a look at a few more. Ah, these are the PLTs. So that's just going to jump to the PLT, right? So if we go XI, let's go 5I. There. B180. Okay, so free at PLT. Free is F0, which is exactly what we've got here. Okay, so yeah, mate, we've got some good progress. We're leaking heap addresses now, which is a win. So we know what the base of the heap is. We've managed to determine that, so that's pretty good. So what I want to do, like we know where free is. dash T. Yeah, there's another way of doing that as well that I have jotted down in some notes. Hang on, let me. This is me doing some other study, but this is useful. Bear with me a sec. I will type it out on screen so that we can all see it. Come on. Here we go. There we go. There you go, Seska. Dash capital R shows the relocation records. Health header.got. Okay. Health header.got. Huh. There you go. So that gives us the entry point. Thank you. That's helpful, Peleus. Yeah, that is the start. So if we did like x 10qx here. Be good if it could space in between. Anyway, Vendetta's here too. Okay, so here's the interesting thing about this, right? When we did the function reading beforehand, we were able to read a heap pointer. You love it, Rasta? Yeah, it's the same thing, Peleus. Anyway, that's useful because at least we get the base address of the GOT, which is fine. No, that's all good, man. So what I'm trying to figure out now is we don't have a pointer to a pointer at this point, right? Like we did have before. So we know this address contains a reference to the PLT. In the PLT, we've got this address reference in the GOT. And inside that, we have a reference to we need basically an area of memory that points to that pointer. Huh. Maybe we can just use that. So if that has that value, I wonder if we can just do the same thing. Probably check the VM map for that. That is, okay, executable code. That points to it. Yeah. Oh well, let's just see what that does. Maybe it'll do what we want it to do. It might not. But anyway, what I'm thinking of doing is func. So once we pull out the address of functions, we can get the address of a pointer to free. And then just see what happens after that. Delete breakpoints. go. Whew. Yeah, so I think we're going to need to do just the same again, which is pretty sweet. So then if we just rec the until running, and we go free address equals exactly the same thing. Getting close, I think. Feeling it in my bones. Ooh. Did you see that? Info function 3. Free is that. Oh, look at that. We got it. Okay, so that's pretty cool. We now have, yeah, we have libc, and we have the heap. So that's pretty sweet. So we've got the leak sorted out, but we need the ability to like do the opposite, right? Actually, before we do that, let's get the offset. Like, what's the base address of glibc? Pwn libc is here. So we need the offset. So if we go that minus this, then we can do some actual calculations. Libc address equals free address minus, oops, minus that. Let's remove some capitalization. Okay, so that means at this point we should be able to do, where are we? So we've got libc equals pwn.elf, and we can point it at libc.so.6. So that'll give us a reference to libc, and then from there we can use our libc base to figure out where system is. So system, I can't remember that. Ugh. How do we figure this out? It's like libc tool for offsets. Oh, nice. Libc, I think you just go plus libc address. So that means, like, if we were looking to do system, all right, let's rerun that, because that will at least give us an idea of whether we're actually anywhere near it. Cool, thanks, Smash. Oof, what did I do? Free address is not defined. Ah, there it is. Yes. Yeah. Got another follower, Jade7. Thank you for the follow. Am I missing the bin as well, am I? Oops. libc bin. Okay, that's right. Maybe I'll just get rid of that and leave it as libc. Yep, cool. Okay. Alrighty, so it's picked up libc. Delete breakpoints. Continue. Okay, so info function system 390. There it is. Okay, so we have system. How exciting. Okay, so now what do we do with it? This is the thing that's going to be a little bit trickier to do, I think. We need to send well, the question is at this point, like, have we ruined things? Like, oh no, it's expecting more input, so okay, so we're at a point where it will at least handle more input, so that's not a bad thing, right? Question is, how do we well, we'd need to get the base of the heap first, right? Which is pretty simple. X 10QX blah. That's going to be 0, 0, right? So I reckon we can probably do we can reuse what we've done before. The difference is that we need to be able to write values. So how can we do that? Okay. So we can define a new function. Okay. Okay, my idea as I'm currently sitting is that we construct what is effectively a fake function definition on the heap. And that fake function definition so you see how we've got this funcdeft, right? It's got a pointer to a name, which we can craft. It's got operations and an op count. So define function. We control this f value. Which can be used as a funcdef. Which then we can associate with whatever the hell we like. And it needs to have there's got to be the ability. Thanks, B-Man. See you, dude. There has to be the ability somewhere. Yeah, no, I don't think so. Well, they do. They take operations, and each operation has an argument. What I'm trying to determine here is this run op. See, we can define a function on the fly, right? And we control this f value, right? Yes, that's exactly what I'm thinking, Smash. So here, all we need to do is mem copy. It's that. That's what we need. We need that mem copy. The problem is that if we can overwrite free, yeah. If we overwrite the free got entry, as soon as that mem copy is done, it'll invoke what we give it. And if old yeah, so I'm thinking if we replace free with system, question is, yeah, we're going to have to define a new function based on the same name as the old one. So all we need to do is specify a name that points to... We can figure out where A already points to, names-wise. And we can write that to the payload. We replace free with system, and free blah will probably be garbage, but then... Yeah, the problem is if you free f-ops... Yeah, that's right. That's right. You know what we could also do is, like, if ops contains any non-null characters, we can just do like a backtick escape sequence or something in that would also work. But so what I'm thinking right now is that we do need to do a define function, and we need to point. Well, basically, we need to do some offset calculations because somewhere on the heap is an A, right? So if we go search mem, it's going to be a lot of those. Search mem A in heap. Right, so that's 1 0 B 0. Okay, so hang on. Is that? That can't be the only place. Maybe what we need to do prior to doing this stuff is like define another one of these so that we've got 2. And then we can try and reference B, because that'll be somewhere in here, right? Disable breakpoints, continue. That didn't quite do what I was hoping it would do. Segfault. I was kind of hoping I could just define another function by another name. I guess it really doesn't matter. We can leave that as is. We can just reuse the A. Hang on a minute. I'm going to get rid of these breakpoints here. So that it just continues. There we go. Search mem. Yeah, so that's definitely the only place at the moment that seems to have A in it, which is a bit strange. What I want to do is have a function because that's the start of the heap. And we know that we're overriding that constantly, right? Oh, no, that's okay. That's fine. Okay, so we leak that heap address, and that happens to be exactly where the A is. So we can write that heap address back to the next round, and that's going to be the name, okay? So that means if we define our function definition is a pointer to a name, pointer to some ops, and a pointer to an op count. So the name is going to be... Righto, so we're going to go... let's do similar to what we did here. Right, so we are not going to replace, or are we? No, we don't need to do that because we're actually manually defining this. So what we're hoping to do is put something in here like bin bash, right? But then invoke the function that we've defined, and we only need to do one lot of those because this is significantly shorter. So then immediately after that, we are going to go, what are we going to do? We need to define a function, and we're going to pass in, what are we passing in? We're so close. I'm not giving up now. We are so close. We need to... Sorry, I'm just thinking for a sec. 3 is there. So that's the... We actually need this address as well. Because that's what we're going to be overwriting. It's the address that we're going to be overwriting, right? We need to be able to write to that location. Yeah, we're going to be overwriting an area of the GOT with one operation. So if we're defining wait up a second. What are we doing? 1, 2, 3, 4, 5, 6, 7, 8. And I will need 1, 2, 3, 4, 5. Okay, so those last 3 need to be zeros. Okay. So that gives us the heap base address. This has been quite a fun challenge, you know. I'm enjoying this. Hopefully you guys are enjoying it and learning something too. Okay, so I know the heap calculation is a little bit dirty, but let's have a look. 2193000. Yeah. So that's the base address of the heap. Okay, so that means what I want to be able to do here, I want to be able to craft. What do we want to be able to craft? I want to be able to craft a function definition which points to the name followed by yeah. The op is going to be I'm going to stash using a NOP. I want to stash the address of the GOT on the heap. Yeah? So that would be the address GOT free. So we have the name, a pointer to the operation, oh, it's doing my head in. Yeah, that's exactly right, Smash. So I want to be able to write to the heap because we need a pointer. Yeah, okay. So what I want to do here is we want the system address to be put on the heap. Okay, because then we know that we've got a reference point to copy from. Okay. And then, like that can just be sitting there. Then we also want to have the ability to point to the area on the heap where we know the A is pointing to, which just happens to be the heap address. So the heap address needs to yeah, so that's going to be name. Then we need a pointer back to this, which is going to be the heap base. And we're going to add, so there's going to be 16 followed by another 8, so it's 24. So basically hex 18. So this pointer points to this. And then immediately after that, we're just going to have 1 because we're saying we only want to copy one op. Yeah? Then when we've done that, so we only define that, we just need to define that function. So if we do an op funcdef, we need to point to, where's the function definition? It's going to be heap address, sorry, heap base plus, so that goes to 18. We just need to add another 16, right? So it'd be 28. So that means we have 1, 2. I guess from here we can just go up, not. Phone.p64.0, and we can do that. Well, we're going to do that 3 times. We've already taken. Oh, so we actually only need 1. Whew. And the new one cannot be larger or it'll realloc. Yes, exactly. Which is, if we only do it once, then we're okay, yeah? So if this is the case, then what we actually want to do, let's take a look at find function. We want to stop okay, what I'll do is I'm going to just open that up for a minute and wait for a breakpoint to be hit. Now, we want to go to define function, so let's go this as define function. So before the 3 calls to free, so it's this bit just before the jump, right? So we don't want the realloc call. So there's the realloc call there. BE8. Yeah, so we want to get to here. That maps to the mem copy prep, yeah? Yeah, that's what we want there. We want to break at plus 201 for define function. Whew. Break define function. What could go wrong? Let's just see what happens. Okay. Well, the fact that we got here is a little bit interesting. Okay, so we said copy pop count times blah. So that shouldn't be very big. I'm not sure that's doing what. Oops. Is that what we copied over? It is, isn't it? System. Wait up a minute. System address. We haven't said where in, like, over the GOT do we actually want to write that. didn't make sense. We did something strange. Oops. Yeah, something's not right. Okay, so we are copying from here, which has got to be a heap address. Yeah, we do. That's exactly what I was just missing. But so have we actually, just going to hit continue. 7.2, so we've specified heap address is that 72260. That's not our call, hey. We haven't even, oh, hang on. We haven't even sent it. So we need to do this. That's pretty stupid. Okay, so when we define a function, we are pointing to this definition here. Now, here's the thing, right? We need to, for a func definition to be overwritten, we want to overwrite the old ops. And the old ops needs to point to the got, right? So how do we do that? How do we do that? So there's a key point that we're missing at this stage, right? We need to somehow get a got address at the start of a function definition. I should say at the second point of the function definition. Because, yeah, the first one is a pointer to the name, the second one is a pointer to the got. Okay, so before we do that, let's just do something fairly obvious. So when we get to this point, we want to say, we want to copy this value here, isn't it? This is the thing that says so I'm going to do this. Okay. I want to see that appear in what we're doing. How did we get here? libc. So RSI F9E. I don't know what that is, but it's clearly way off because there's nothing here that resembles that. I say that we stop on op-nops because we should see a few of them, right? So we want to go to constant, subtract, divide, no op. There's going to be a couple of nops in this function, isn't there? So disas run op. Look for the nops. Got to be here. Yeah. So we want to break there. It's 514 actually, isn't it? Right. Run up. Okay. So we'll let that run. Let that run. Let that run. Okay, so we have spat out system address. So our next NOP let's have a squiz at the heap. Can't see a heap pointer anywhere in the registers, can you? 1E. Here we go. X 40 X. All right, so this represents what I would assume to be our payload. Yeah, we should see an op system op heap 41414141, which I assume hasn't happened yet. Where did that stuff come from? That doesn't look... Ha! Ah, there it is. Right, so... we have... system address should be after that first NOP. Which is here, right? Yep, that's the entry point for system. This, that should point to A. Okay, that's good. That's clearly a pointer to bin bash. Righto, so we have another NOP. Now what are we doing? We are running another op. Which is another NOP. So yeah, another NOP. Let's get to, like, so the next operation that's interesting is the 41414141, right? So let's so another NOP. How many NOPs did we do? Ah, here we go. So this should pull racks out. Okay, here we go. Right, so that's what we wanted to see. That'll give us our second invalid operation. We're making progress. So Why is it only showing me bytes all of a sudden? Okay. That makes no sense. All of a sudden, we're not seeing anything 64-bit. This is confusing. Anyway. Right, there it is. That's better. Six, 6, and 5. System address. Come on. Okay, here we go. Right, so we have what is effectively, we've hit a NOP, which I assume is going to be for this thing here. So next we should hit this NOP, then this NOP, then this invalid operation, then this function definition, which takes us to 2.8, which points to this. So hang on, 1.8 points to that. So I would assume that. Oof, what is that? I've got my calculations wrong. So it is worse than doing a rock chain. So we want a NOP, and then there's the system address, which comes straight after that. So that's going to be system. Yep. Followed by the heap address that should contain the letter A. Yep. Okay. So we're up to 3.0. Oops. So we're up to here. Which should take us to another NOP. Yep, NOP. Lead ret. So that means we should now get to here, and we should end up with an invalid operation. Because this pointer, so that's the heap address, then there's the heap base plus 18, which takes us to that. Yep, so that's good, I think. What are we crafting again? So we've got the heap address and the heap base followed by 1. Yep, so that's... Yeah, okay, that makes sense. And then we define a function that points to 28. 28 starts there. No, that's not right. It should be 38, not 28. Cheers all, thanks for sticking around. Yeah, that needs to be 38. Good night, folks. Thanks very much. I appreciate your patience. Ooh, we're defining a function now. So we're in... probably deal with just having half that many.
Tell me somebody how long he will be on my mind.
That's what we want. Okay. So that points to 1.8. That points to EB0, which is there. And that points to 3.8, which starts there. Okay, that makes more sense. Let's just see where we get to. We are doing a not. And we are doing what looks to be another not. Yep. And then this one is going to be an invalid operation because it's invalid op, which would be for the heap face plus 18. Right, so that was this one. Next we should see a function definition. Call define function. Okay, so here we should actually see it. Dereference and do a string compare of A and A, which it should find. It should then pull out according to here. Okay, pulls out the function definition and checks the two op counts, and the new op count should be less. Rex, RDX and Rex. Yep, so RDX is definitely smaller. So, mem copy. Right, so I think I know what we need to do here. So we're at the point now where we are copying. We're going. Oh, we've got another follower, Arkash. Thanks for the follow. So we're copying. From here. Is that what we wanted it to be? Yeah, so this value here points to that, which is the pointer. Is that right? I think that needs to, yeah, that needs to be 28. Which means I got this bit wrong. So that needs to be that. Okay, so that mem copy should have succeeded. Hey Luke, how's it going? Bitwise is here too. We're getting very, very close now to owning this thing. But I think one of the key points that we're missing so far is that we haven't written a GOT address anywhere that's useful. We're currently finalizing. Oh shit, we are 5 hours in. We're very close to finalizing a PicoCTF 2018 challenge. But I'm super close. Super close. Bitwise, thanks for the sub, bro. You're a legend. Thanks for your support as always, my friend. So, the only thing that's missing at this point is I need to define a function so that when we're copying from the old operations, sorry, for the new operations to the old one needs to point to the GOT. So, how are we going to do that? Yeah, Luke, there are a number of things that you could do to get started. I would recommend starting, well, it depends on the kind of work that you want to do, but general pen testing related stuff, go and read up on things like Hack the Box tutorials, go and play with VulnHub virtual machines. They would probably be the best points to start with. Maybe consider studying for things like OSCP. But I think go to vulnhub.com and go to Hack the Box and start playing. That's probably the best place to start. And then when you start playing with those things, you'll find yourself digging up references to help you figure out how to own those machines, and you will learn. VulnHub is really good. Right, so how am I going to get this thing to contain a reference to the GOT? I need to somehow redefine something to point to the GOT. What are we going to do? What are we going to do? What are we going to do? Pretty sure that's all we need. As soon as we figure out how to point, like redefine that function, maybe what we need to remember when we use the admin to, oh yeah, man, blast from the past. Seems like a lifetime ago now. How are we going to write this value? Yeah, that's true. All right, so I think what we're going to need to do when we redefine I think what we're going to have to do is when we redefine this function here, I think we're going to need to put like we're going to have to put some like maybe define a function here somewhere, like point to the got in here. Do you know what I mean? I'm wondering if there's some way that we can do this here. When we redefine that function, it needs to yeah, what I'm trying to think is once we've redefined that A function, which we're currently using, is there anywhere that we can... Because remember, like, we end up here and we realloc, right? And we want this to point to somewhere that we control. So how are we going to do that? How do we get op count? Oh, yeah. Yes. We just do exactly what we've just done. So here, we know what the GOT address is at this point. So all we want to do really is define so if we go func def and we point let's just point this at ADDR got free. Yeah, let's try that. Feel like we're super close, hey? Ooh. I can't type to save my life, clearly. Ooh, what happened here? Oops. Okay, so Broken Syntax, hello, how's it going? I think I'm gonna have to change this around. Super close, maybe I just need to keep that down there. Well, actually, maybe I need to do the not thing. Work and such, yeah, man. Documentation for the win. There we go. Okay, here we go. Now, what we need to do, I need to validate that. Okay. Where's our heap address? Our heap base is here. Okay, so that's our fake frame there. Good night. See what we're up to, I think. What are we doing here? Ooh. Jump. We're doing a, doing a invalid op. Yep, that's fine. Ah, crap. Yep, so that's fine. So that means we have just done this one, and we should be defining this one now. Excuse me. Haha. Stick at it, Luke. It's worth it, mate. Okay, define function. Is it going to do what I want it to do? 7 jump racks. Here we go. So call define function. Okay, here we go. So now we should be checking again and making sure that that's the right one, which it is. So it should be pulling out, comparing 8 and 1, which is fine. Mem copy. Bugger. I'm so close. So we know that the function definition for this... Ah, hang on. Did that just pull... So we did... Five, 0. So then we need... One, two... Yeah, so that's the God address that we need. So we need... It'll be zeros, then 0, 0, 21. Get rid of these times.
Yeah, not good for me, I know. But I feel like I won a lotto.
21. This is going to be heap address again.
Need to test and prove, I know. Love to stretch the truth, I know. The devil dressed like you, I know. That's a blessing too.
Oops.
We go down that rabbit hole where there is no giving, just taking. Yeah, you love it though, cause no good habit is for breaking. So let that liquor pour down on your chest right from those lips, and we can blindfold all our problems. We can't lie, we love this shit. Yeah, you gotta have yeah, I gotta have it. You want it, you grab
I'm so close. I'm so close. Thanks, Vendetta. Oh, you're still with me, dude.
I want it, I grab it.
Oof.
Always had a taste for the poison. Yeah, I can feel you in my veins. The key is right there.
Did that not work?
But I've gotten used to the change. They think that you're killing me slowly. I think you should sharpen your fangs. You don't have to ask where we're headed. You know where we're
That's
going
upsetting.
today. Down that rabbit hole where there is no giving, just taking. Yeah, you love it though.
Dude, I'm so close. I know I'm close. I need that invalid operation.
Those lips, and we can blindfold all our problems. We can't lie, we love this shit.
We're gonna get another one. Holy shit, that is so annoying. Is that because I'm writing too many bytes? So there's 16. I can write 80, yeah? 1, 2, 3, 4. Let's make this super clear. 1, 2, 3, 4, 5, 6, 7.
Yeah, you gotta have it. I want it, I grab it.
This is so fucking annoying. Ah! Just had an idea. Is that Sigabort? Yeah, it is. So yeah. If I could write those extra 2, it'd be a different friggin' story. The problem that I've got is that when writing this func definition here,
I could tell within a moment you knew me well. I could see you gave me solace when I needed someone there. In the darkness I still see you like a golden arch, rising high above the sunset in every way you are. I know that everything's in focus now. I'm seeing you for the first time today.
so close. Yeah, that's what I'm trying to figure out, Smash. Is it actually... Where does this actually end up? Anyway, I'm gonna get rid of this stuff. Don't need those things. I might go 40 this time, because something in here should have written the got address somewhere to the heap, right? And the got address is what was it again? 601B80. Can't see it anywhere in here. 601C60.
All the days when I was searching for some kind of sign. Now I've reached the destination with someone of my
Is there anything in here that in any way resembles?
like an LED.
Where do we attempt to write this to? Was it to the heap? Or is this to the global pointers array? Maybe that's what we should be looking at. Do we need to run a new func command down the bottom to trigger the double free? I don't think so. C6. Let's just do this for a minute. Would you look at that? You see that? It looks like we've written it here. Binary isn't PIE. Yeah, I know. Yeah, no, I can see that. The problem that I've got though is that I want 601C70. Is that what I need that to be? Were 87150. This value here has been written by me when we did this. Address of functions 601 C60. Oh no, hang on. Got free. Got free is 1B80. It's there. It was written there. Okay, so we have the ability to write it there. Does that mean that we need to craft a function we need to abuse this, I think. Yeah, because we are defining a function at this point that says point that function to the got. So if we could define a function we haven't leaked any addresses at this point other than that's giving us the heap address.
Watch the world pass me by. Black hole trying to chase a sunrise. Every day I was on my own. Can't see my hurt cause I'm a ghost. In the crowd I still felt alone. Yeah. But then we found each other and everything turned around. From broken heart to another. You never let me down. You never let me down. Ooh. Even when my world gets all fucked up and comes crashing to the ground, you never let me down. You never let me
I reckon we can get rid of these knobs.
Blue skies never look so gray. The brighter the stars, the more I just fade. Couldn't see how anything changes. Some days I could barely wake up. The voices inside, they told me give up, and I almost
Sorry, I'm in thinking mode now. Why did that not do what I wanted it to do? Sorry, there's a primitive that should let us do it without heap corruption. Yeah, so I'm confused as to why all of a sudden the thing that I was... Ah, there it is. So that was 601. The 80 was being point to 601.70. Based on what I wrote here, system address, address. Ah, that's me doing the copy. So that's put, I'm confused a little bit by that. That's putting the got free over to defining a function. Okay, so that's base plus 38, which is oh, so confused. Yeah, so that was the 0 and the 0. That says define a function. 17a. Define function at 38. which says whatever A points to. How is another function being defined at this point?
My shadows, they follow you like an accomplice. Lost all of your dreams, the night is heartless. My shadows, they follow you. My shadows, they follow you in the darkness.
We're getting close. I know we're gonna get it. I know we're gonna get it. How is that getting written here though? It's gotta be that function definition here, right? We're defining a function and we're saying define a function at this location, which is pointing to this location here, right? And that function definition says heap address, which points to the letter A, heap base, which points to the system address, so that's the operation, and that's how many. Heap base plus 28 points there. We're saying define a new function. But that is not a heap address. So where is that coming from? That's 601 B80. That is pointing to the God. Like that's the God entry for free, right? Or is it the PLT entry? No. Maybe it's not that at all. But hang on, 601 B80. Yeah, that's... Ah, okay, there we go. Yep, so that points to system. Sorry, no, that points to free at the moment. So we kind of want to effectively do exactly the same thing. I'm really confused as to why that's been written there. Because when you define a new function, okay, so Just gonna stash a copy of that. Because I think we're going to have to try and define more functions up front. Okay, so I broke something clearly. Get the heap address. All right, so just gonna experiment because I'm confused. Sorry if I missed something, but immediately after we've leaked the addresses, is there already a function def object that exists at function x, which is an ops pointer to the GOT? No, that's the thing that I'm confused about, because the only thing that could write that there would be, if I go back to what we were doing before. So we write that here, right? We define a function at this point, and I was thinking, like, if I do the same thing there, we should see two entries to it, right? At this point we should see it, but it's not there. Yet if we continue, oh, hang on, zigzag. So we're back to the problem that I had before. Something in our little chain of Shizen has caused a problem. And it's only when I add another function definition. There you go. Now it's written there, and that's okay. Oh, I know why. That's a problem then. Thing is, I kind of want something, our function definition, to contain a reference to this. Because we need this pointer to be part of the function definition. Oh, hang on a minute. I have an idea. Actually, do I? Yeah, okay, because the function definition have the pointer to the ops and then a count. I wonder if we could do... Oh no, because when we do like specify a function definition, I was thinking if we could write another one here, which we can. So if we just do this, that should probably work. Okay, I think I have an answer. Okay, so this heap address, that needs to point to that function address there. Basically needs to be this value. So if we go that minus the heap address that we get out. So that's the offset. We just need to add that. Plus OXA, is that what it was? Yeah, A0. That stays the same. I think we're on something. Yeah, okay, here we go. Only one funk diff, so it's not that one. Great song. Okay, so we're getting pretty close here. Hey, Goji Man! Long time no see, man. I'm doing really good, mate. How are you doing? Yeah, Peleus is here too. Clearly that didn't work as expected. Yeah, mate, from 2018. Okay, so that's the first invalid op, which is the heat base. There's thin SH, then there's running A. You get the heat base. Then there's funk def straight after that, right? So come on, funk def. want to get to that mem copy. Maybe what I need to do is break on define function. Here we go. So this should be checking via a string compare. That's my problem. It's the function that I'm trying to define. So they're not the same. These are the same, and I don't want to be redefining that. So that's not right. I've made a mistake, and it's to do with that offset calculation that I did before. So this God damn it, that is really not what I was thinking made sense. Yeah, hang on. So that value there should be a pointer to a string, right? So that should be garbled junk. Now for us to define our function, we need garbled junk on the heap. Right, so if we come back to looking at the heap, which is here, we're defining a function from 38. Now 38 starts with the same pointer. Right, that pointer there. Right. So remember, we've got a pointer to a name, pointer to the ops, pointer to the op count. 28 is there, and that's the pointer to system. This pointer is correct. See, we loop through and do a comparison. Why is it that it's invoking A? It shouldn't be, oh yeah, it should be running A. And now it's overwriting A, which doesn't make any sense. Oh no. Something's up here, this doesn't make sense to me. is it comparing those two? That doesn't make sense. When we define this function, we point to heat base plus 38. That's 28.
All the days when I was searching for some kind of sign. Now I've reached a destination with someone of my kind. Keep me breathing with a feeling.
Let's do that one more time.
LED light. Now
I think I'm onto something, man.
in shadows, you woke me up tonight. Everything's in focus now.
Okay, so if we have a look at this. Right, so this is our list of functions. I've got 2 extra functions defined. This one, these are both pointing to the GOT, but I want this to be a fake function definition. Right? This is a fake function definition. Is that what I'm doing wrong? I need to define another function. Yeah, that's what I need to do. I need to define a function which is this. Plus 1, 2, 3 lots of 8. That's my mistake. So basically the address of functions, that's what I need. Plus 24 bytes.
Just another night, no sleep. Staring at the wall again. Always know that I'm in deep. When I start ignoring all my friends. I don't even know the problems. So how am I
Okay, so that's not doing
still I'm drinking like it stops 'em. I feel too
doing what I wanted.
nothing at all. Lately, I've been a little crazy. I wish someone could save me now. I can't take these emotions, damn these emotions lately. Now I don't even know myself. Keep wishing I was someone else. 'Cause I can't take these emotions.
This is really quirky. I think I might know what's going on. Okay, so I need that to be a pointer to itself. So that means Godfrey plus 10. Nope. Functions plus why is that zigzag? Zigzag. I don't understand why. Man, I'm struggling. Okay, Smash, thanks, dude. Zigzag. Thanks for your efforts, mate. Okay, so let's put that back to what we know doesn't cause a crash. Okay, so that's fine. Ooh, okay, hang on. Yeah, man, I do have work tomorrow. Yeah, it's going to be a bit rough. Why are you crashing? It's in define function. Oh, I think I know what's going on. Yeah, that's it. It's gonna happen. Okay, so we've created 4, so that's perfect. Now I'm going to create another 2.
I always felt like I'm on the outside, never fit in, watch the world pass me by. Black hole trying to chase a sunrise. Every day I was on my own, can't see my hurt cause I'm a ghost. In the crowd I still felt alone, yeah. But then we found each other and everything turned around. One broken heart to another. You never let me down. You never let me down. Ooh. Even when my world gets all fucked up and comes crashing to the ground, you never let me down. You never let me down.
Okay, so why is that still breaking?
Blue skies never look so gray. The brighter the stars, the more I just fade. Couldn't see how anything changes. Some days I could barely wake up. The voices inside, they told me give up.
PicoCTF. Why is that not there? There it is.
Even when my world gets all fucked up and comes crashing to the ground, you never let me down. You never let me Even when my world gets all fucked up and comes crashing to the ground, you never let me down. You never let me
Get your body on my body. La 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 la. La 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 la. I know you want me, baby. Let's stop talking. I'll be in my zone till you take me home. I know you want me, you already got me in my zone till you take me home. Get your body on my body.
Yeah, I know, it's killing me, man. There must be bad characters in here or something, but I don't know what it is. Bad characters. Okay, so we know that works. What I want to know is if I add another function here, does that work? No. Ah, it's because of the way that I'm reading. Might be onto something here. Another follower. Thank you for the follow. I think we're super close to shells now. So I'm thinking what I need to do is to have this point to, like, so we've got a fake thing here where we're copying to this, which points to that one, which is the first one that we're basically, whatever that last one was, this one here is what we need to point it to. So if we define with a name of that, That's not what I wanted. That's better. Okay, so we've got this fake frame. So this fake function definition has this, which points to that. This, which points to the got, and this is a fake size. So then as we're going through, now I need to set a breakpoint on define function. Okay, so when we get to the string compare, here we go. This is more like it. See your broken syntax. So that's not going to work. This one shouldn't work either, because that's pointing to a heap address. This next one shouldn't work. That is the pointer to free. Yep, so we skip that. And then this next one, we're getting closer now. Oh, did we mess that up? So what we were defining was 1C70. Oh, is that what I wanted to do? No, it's this one. 68, not 70. Fuck. Just functions plus 8. Crap. So close. Assuming this works. Break. Okay, so if we look there. Oops. And then CX. Alright, so what we're saying is we point to C68 just like this one does. C68 refers to... Oh, hang on. That's not what I wanted. I need that to point to 70. Because that can't point to itself, right? Because 8 points to that. Another follow, Cybergaia. So kind of just need padding in there, like 6-0, so we can do addressive functions. Which puts functions in there. That was the 80, then that would need to point to 78. Oh no, that's okay. Yeah, that's okay. Oh no, that is a reference to... That's used as a pointer back to that. So that has to work as a function pointer definition, which would point to that. Point to itself. Needs to point to itself. Which I don't think is going to work. Yeah, it's because RSI is nil. Yeah. Okay, so that now actually makes sense. Unless... Yeah, okay, so we need to... I do need to pad this out with more functions. Okay, so... So I do need to do that, and then I should be able to define a function. Oh no. Right. I know exactly what's wrong. Bit of rest is warranted. Come back. No. Sunken cost fallacy, mate. What I need to figure out, and this is the last piece of the puzzle, is just like, how do I write to $7 hours, hey? Yeah, it's true. I'll call it at 7 hours. If I haven't got it in 20 minutes, I'll go to bed. That pointer needs to point to a valid function definition. And this is the only part of BSS that we can write to. So that means if we defined multiple functions here, and then when we define the function again, yeah, that's not gonna work. So to define. Define Godfrey. And then we define a function that is 68. And then we need that to be 68 as well.
Make the ground shake like a fucking earthquake. Make the ground shake like a fucking earthquake.
Okay. String compare. Not going to be the same. Not going to be the same. It should be the next one, right?
Make the ground shake like a fucking earthquake.
Did that not do what I wanted it to do? Run off. So if we have a look, yeah, right, that didn't do what I wanted it to do. So it was this, right? It said point to 38 601 C68.
Make the ground shake like a fucking earthquake.
Oh no. That needs to be that pointer. Right, so I'm back to where I was here, so it's not address functions. It is heap address plus A0. Okay, so we should have 196D150. 196D150. Copy that to that location. Okay. Come on. Gotta be close now. This will be the next one. Here we go. They're the same. We should get to a mem copy next. Oh. It worked. Oops. Ah, shells. We got shells. Ah. It worked. Oh my god. Holy shit. 10 minutes to go. Let's see if we can actually get the flag out of this thing. Woo. Man, I thought I was going insane. Sorry about me being super quiet, because I've been concentrating and I feel like I've been battling. Okay, so let's go. P equals phone dot, is it remote? Yeah, that's a great question. Oof. What did I do? I missed a comma. Oh, yay! Woohoo! Check it out. Yes! Fuck yes! My God. Ugh. Fuck. That was brutal. Man. Winner, winner. We actually got the wootage at the end. Holy shit. Bruh, man. That was hard. I really struggled to get my head around that. I felt like I don't know. Like it seems so simple now, and at the end I was like, oh, I can, and yeah. Does anyone need any explanation as to what the fuck we just did? Rasta, we got shells, dude. We got shells. Check it out. Where are we? There it is, boy. The TLDR. Okay. So, the TLDR is this. You basically have an area of memory that has a collection of function definitions, okay? And you have the heap. And what you need to do is you create up front a couple of function definitions that have a number of operators associated with them. And then you make sure that in your exploit, you see the first thing that we send down here, where are we? This send line after. This thing here is intended to, this defines a function with a set of operators that reallocates the same memory buffer as the input, so the double free doesn't actually kick off. So then you can reuse that. And then from there what you do is you reuse your function definition, which now points at the heap that you control. And the heap that you control has all of your operators in it. And using that function with all these operators, you can say, I want to define a new function. And what we're doing is we're actually inserting into the function table a pointer to the GOT. So a pointer to the GOT that contains the reference to free, right? And then around that, we add another couple of values to make it look like that thing itself is its own function definition. And then when we go further down, after we've leaked the addresses because of this funk stuff that we've got going on here, we then basically do exactly the same thing again, but we define a new function definition with the same name as the pseudo function definition that currently points at the GOT. And then when we say, please go and redefine it, what happens is it says, okay, do we have more or less operations than we had before? We have actually less. So all it does is it says, okay, we'll take the contents of your operations and we'll overwrite our current ones. Well, ops here at the moment contains our reference to system, and old ops is currently appointed to the GOT, referencing the contents of free. So at this stage here, we actually overwrite the entry for free in the GOT with system, and then we call system ops, and then system name. And system name just happens to contain, I think, no it doesn't. Ops contains, one of these contains the string that we control. And we end up with, the fact, because in our exploit we have bin bash, it executes bin bash under system. Yeah, does that make sense? Yeah, pretty much the same as what you're gonna do. Right. It is nearly 3 a.m. I can't believe you have all stuck it out with me this far. Much appreciated. Sorry for the last couple of hours. I feel like I've been in my own world, and I haven't really been describing what's been going on in my head, partly because I didn't really know. But at the end of the day, we managed to solve it, which is fucking exciting. Despite the fact that it's nearly 3 a.m. and I kind of thought maybe we'd do a 3 or 4 hour stream. So, woohoo, win. I will love you and leave you guys. Thanks again for the support. Thanks for sticking it out. Ping me on Discord if you have any questions. Thanks again to everybody. Time for bed. Be good to each other. Good night.